tracking and PPT, renewable energy and energy efficiency. He is a chartered engineer and fellow of the Institution of Engineering and Technology. He is an associate editor of various top journals such as the IEEE Transaction on Power Electronics and the Journal of Power Electronics. And today, he will be talking about power converter for energy storage applications. It's not? It's fine, yes. Well, the floor is all yours.
Assalamu alaikum wa rahmatullahi ta'ala barakatuh, and very good morning. Thank you very much, Francisco, for the introduction. Can we have the slides, please? Yeah, so there is some adjustments on the title of the talk, which is supposed to be I call converters for energy storage, but actually I have changed the title, which is the role of power electronics for providing sustainable energy supply. So what I'm going to share with you this morning to see how the power electronics play a major role in providing a sustainable energy supply. Because I think we have moved from the era of the need for energy. I think now most of the people have energy. But is this energy that we are using is sustainable or not? How long it is going to last? And if we can see the crisis that happens around the world is always affecting the energy sector. What's happening now in Ukraine, you can see the whole Europe is worried what will be the energy supply in the next coming couple of years. So as researchers and as engineers, we have a role to play. We have a responsibility to fulfill, which is providing people with innovative and solutions that are sustainable. So as a power electronics engineer, I want to show you on how we can play our role and how we can help the people in achieving this objective. All right. So the outlines, there are 4 outlines, very simple, which is energy and environment, which is an issue. The relationship between the energy and environment is a very complex and difficult balance. Which one you balance, the energy or the environment, how you can fulfill the both requirements. And then we look into the challenges. There are a lot of challenges in achieving sustainable. Many countries have already achieved energy access to people, but they have not achieved sustainable energy access for their people. And that's the big questions that we have to answer in the future. What is the challenges in energy conservation? This is a very important topic, which has been forgotten for people talking about renewable energy, people talking about how we can increase the penetration of renewables. But they forgot one very simple, basic aspect, which is energy conservation. I'm not sure how many of you knows what is energy conservation, but I will talk about it later. You know, it's very important and very effective. Actually, it is maybe better than doing renewable energy because it's a zero, sometimes it's a zero investment. You don't have to do anything. And you can sustain. And then we look into what is the grand challenge. All right? So if we look into the environment, what we have, some of the facts, we will be very soon around 9 billion people. So the world population is increasing. It's a fact. What else? We will be the energy consumption per person. That is a very important aspect that we consider. Yes, the population is increasing, but the energy consumption per person is double. So the population increases by 20%, but the energy consumption per person will be 2 times what we use. And we can take a very simple example. 30 years ago, just I think most of you may, I don't know, maybe 30 years ago, how many of you have a handphone? None. Right? How many of you today does not have a handphone? If you don't have, I can give you mine. None. None does not have a handphone. So what does it mean? It means that it's energy. How many of you does not have a car? How many of you does not have a laptop? How many of you does not have a TV at home? 30 years ago, we don't have a TV at home. Many families does not have a TV at home. How many of you 30 years ago does not have a washing machine? Maybe all of us. So what does this mean? It means actually our life is becoming dependent on appliances that requires energy. So, and the future will be more. Our consumption of energy will be double. And I can give you an example, about myself. I came from a very small town in Algeria, in the northeast of Algeria, Sétif. Not from the capital, Sétif, but from a very remote area, Sétif. In the 1970s, the whole village, small area, in the mountains, the whole village, we have one car. And that car used to be for everything, as an ambulance, for waiting to bring the bride, for emergencies, everyone goes to that person, please bring this to the hospital, please. One car in the whole village. I went back to the same place 40 years later. What I found a village of cars in one house. You cannot find place to park. The whole street, small street, the village. And the cars are, every house there are 4 or 5 cars. What does this mean? Maybe people getting a better life. Economically, they are well, so they have a lot of money to buy cars. But from our perspective as engineers, as a research engineers, the energy consumption per person has increased. So this is the fact. And it happens everywhere. I think in Saudi or in every country is the same thing. So the energy consumption is increasing day after day. And it will be doubled. All right? So, and also, one of the facts, 65% of the global warming is due to the energy use and the energy generation. Means the way how we use the energy and the way how we generate it is not efficient. Means, what does it mean? Means when we burn oil and gas to generate electricity, there are a lot of losses. There is emissions. So we contribute significantly during the generation process, and then during the transmission of this power, and during the usage of this power. When we use this power, also the loads are not efficient. So we can see the process, that's how much we contribute to the global warming. All right, so what's the impact? I think we can see it very clearly. The weather pattern change. Every place in the world, they're experiencing either very extreme, very hot summer. Sometimes during winter, it's summer. You cannot differentiate between seasons. We used to know there is summer, spring, autumn, very, very clear. But now, during summer, I was talking to my mother a couple of days. You see, during the whole winter, there is no rain in Algeria. When summer comes in, start the rain. And that affects the agriculture, affects the ecosystem, So that's actually what we see. We see there is a lot of sea level rise. Sea level rise, this is, I don't know, you know this or not, but I have visited Bangladesh. And this Bangladesh, during the raining season, 25% of the country goes underwater. 25% of the land of the country goes underwater. And it's increasing year after year. There are many countries around the world, they are already experiencing the sea level rise. All right? What else? Okay, in the past 50 years, the world have lost 25% of its topsoil and 30% of its forest. And all this due to the need that we do. And also, excuse me, I have to use this too, but what's the biggest worry? If we continue as normal, business as usual, we will reach to a state, we call it the irreversible state. Irreversible means whatever you do does not make any difference anymore. So if you want to act, we have to act now. If we want to change, we have to change now. Because this is the time where if we make a change, we will see the impact. If we pass this, there will be too late. So these are some of the facts that we see. Also, this does not only affect the land, like we said just now, the topsoil, but also we are affecting our marine life. So the acid levels in the oceans is increasing year after year. And you can see in this figure, the darker the color, the higher acid levels. So actually we are affecting also the marine life. And whenever we open the TV in the morning, we see floods. If we don't see floods, we see droughts. So there are areas which used to be very green, suddenly become very, no water, no access to the water. Many countries have a problem of access to the water, you know. Even in North Africa, Algeria have problem accessing to the water. We are using desalination water to drink. I think Saudi Arabia, there are so many areas in like, Riyadh, I think, it's using desalination water. Maybe Ha'il here is very lucky. They have very good quality water. But there are many areas that have a problem of shortage of water. All right? Weather, earth temperature. Earth temperature is increasing, and it has a lot of effect. And in Europe, in 2011, more than 20,000 people died because of heat waves. And it's every year, especially the elder people, which have not been used to this kind of weather, they cannot support it. And it happens in 2019, I was in one place, in Europe, in France, which is called Grenoble. I don't know, you know it, Grenoble. You know, Grenoble is the Alps, where people go for ski, you know. It's in the mountain area. The temperature reached almost 42 degrees. People never experience this in their whole life, they say. We don't have air conditioning. People start installing air conditioning because they never experienced this before in their lives. For the last 50, 60 years, they never experienced this. Grenoble, even in summer, the snow is there, you know, because it's a ski place. So it's the same happening every part and in every place in the world. So this is what we experience. So I think in terms of renewables is the solution. As we can see actually from the presentations of yesterday, Haitham and Saeed, and there are quite a number of what you call projects that's happening around the world. Renewables, it's a solution. It's a part of the solution. But as I said just now, energy conservation. What does mean energy conservation? Energy conservation means use energy as you need. And unfortunately, yesterday, one of the maybe not a good example for energy conservation. Yesterday, we was freezing in the hall. Temperature, I think, was 16. That is not energy conservation, because to bring one temperature down, it consumes how many kilowatt hours to bring 1 degree down, or 0.5 degrees? It consumes maybe 10 to 20 to 30 kilowatt hours, depending on the size of the system. And why we have to keep the temperature 16, and then we try to go and buy a jacket with $100 to keep us warm? That's what we do. You know, we keep the temperature low, and then we buy a jacket to keep you warm. See the contradictions? You know, so that's the balance. And that's energy conservation. And this energy conservation, should be a way of life. Means the day that you live, you have to apply conservation. Means you want to walk, for example, to purchase something. If you can walk, it's better. That is energy conservation. If you boil water to make tea, why you have to boil 2 liters to make a cup of 250 ml and let the other water cool down, and then you heat it later? That's not energy conservation. When you sleep, why you leave the light on? Don't worry, if the thief comes, does not need your light. He has his own lights. So this is energy conservation. I know from the person perspective, it may not make a difference, but multiply 1 bulb by 8 billion bulbs in the world. You can see how much we can make difference. When you leave your office, where you leave your laptop on, if you switch your laptop off, you save around 75 watts to 80 to 100 watts of electricity, multiplied by how many laptops around the world. That is energy conservation. You know, this is energy, means you have to apply energy conservation, because there's no point talking about renewables and then use that energy to be wasted. So we are wasting double wastage. So, and I like this statement by the ex-United States President, Jimmy Carter. And this is the type of politicians we should have. Energy conservation is an act of patriotism. Means if you love your country, if you really care about it, use energy efficiently. Yeah, we have so many acts of patriotism. We go a flag and go to the football match and support and waste a lot of time and money. But this is how you support your country, how you love your nation. Use energy efficiently. Because when you use energy efficiently, you will save the money for the country, you save money for the people, you will save the environment, and so on and so forth. And unfortunately, even in the United States, after this, the last president, Donald Trump, was the opposite. He pulled out from all the conventions for the environment. So this is the politician change. And that's actually impact the science and also impact the direction of the countries, right? All right, so Alhamdulillah, Allah subhanahu wa ta'ala has given us resources. A lot of resources, which we don't use. You see, if we only look into the sun produces more from the solar, more than 2,850 times of what we need of energy. Almost 3,000 times. If we use the lowest one, the resources available in hydro is enough to supply the whole world of what we need of energy. All right? And I like this. This plane actually in 2011 took off from Abu Dhabi, and it makes one big round across the world and come back to Abu Dhabi. You know, it's 100% full of power. You know, and I know it's still far from the commercial application, but maybe one day we will have some of the energy we use. It will be used from the solar. And the good thing about this airplane has taken off and land so many times, because there are many planes take off, never land. So this have taken off many times, and it's proven to be one of the niche area to be used. And this one, I know maybe, this is a statistic done by, I don't know, you know this, QCell. QCell is one of the Korean solar manufacturers. They do, oh. Okay, I can't be here, I don't want, I have two in my hand, I cannot hold another one. So I lost control then. I have only two hands. So this QCell, it's a solar manufacturer. They fabricate solar cells. I don't know, in Saudi here we have, I think. It's a very well-established company from Korea. They produce solar cells. So they have done study for their cells. They produce these monocrystalline solar cells. They operate around 15% efficiency. So based on their study, they say if we install this amount of solar, I don't know, you know Algeria. This is the map of Algeria. You know, it's a continent by itself. So if you install this amount of solar, of this type of solar panels, will be enough to supply the whole world of electricity. If we install this, will be enough to supply the whole EU, the European Union. If we install this, we can supply the MENA region, the Middle East and North African countries. Let's assume this company is making promotion. It's just a publicity. Let's multiply this one by 5 times or 6 times. Still is possible. You see the resources available. And the good things about, if you look into especially the Arab countries, and you look into the time zone, we are almost shifted by 2 hours, 3 hours. So that's actually enable us, if we have like, all the Arab countries are connected, we can make use of the solar during the whole day. And then we can use the peak, for example, in Saudi Arabia, to supply the the peak load in Algeria or in Morocco. In Morocco, you used to supply the other parts of the part. So the link, these connections, actually is very, very strategic, and it's very useful. But yeah, in terms of, I think, technology, this is a very well-known slides which we extract. So in terms of efficiency of solar cells is improving, and which is very good. So we achieve almost now, we're talking about 26% solar cells efficiency. We are looking to hybridization. No more only one system works at the same time. So, for example, this one is a dam, and then on the roof, on the top of it, of top water, there is a solar panel. So we can use both. We can use water as a resource for electricity generation, and you can use also power. So this is actually minimizes the cost of the systems. And you can see also the cost has dropped from $76 per watt in the 70s to today we're talking about 20 cents per watt. So it is very, very important. So in these photovoltaic systems, so now we start talking about power electronics. So if you look into this different configurations of the power electronics photovoltaic systems, what you can see, there is one common thing. You can see here? Photovoltaic systems will never work without power electronics devices. Whatever you're talking about what you call watts level or megawatt level. So in order for the renewables to work, especially for photovoltaics, in order for you to connect it to the grid or use it, you need the power electronics devices to interface. So that's a requirement. Even for large-scale solar systems, also in order for us to transmit or to transfer this power, we need this kind of power electronic devices, actually, even for the HVDC transmissions. Wind. Let's look into the wind. You know, the latest wind turbine is around 10 megawatts. You see the power density when we reach 10 megawatts. One wind turbine can generate up to 10 megawatts. You know, so in terms of cost, what we call dollar per watt has significantly dropped. And we see this kind of, especially in Europe, many countries, especially in the northern part of Europe, they're installing a lot of wind energy. And there are some leading countries like Denmark, they already achieve almost 50% of their electricity consumption now is from wind energy. Means, what does it mean? And they have a target to achieve 100% of electricity from wind. Means it is possible. All right? Yeah. So you can see here the target. The Denmark, they want to achieve by 2050, 100% of electricity used will be from wind energy. There are leading countries around the globe. Many of them are especially in Asia now. The leading countries are in Asia. China and India are one of the leading countries in the wind installations. And this is just a chart of the dominant. Also, let's look into the power electronics. These wind turbines, you can see now, we have reached from zero power electronics in the wind conversion system up to 100%. Means now the power electronics converters are able to handle 100% of power that is being generated by the wind and connected to the grid. So what does it mean? It means wind turbines are very dependent on power electronics. So both solar and also wind. All right, so there is also a lot of research on the different types of wind turbine designs because, you know, designing the buildings is no more designing boxes. When you design a building, you have to make sure that this building is sustainable. Means it generates certain amount of energy that it's used. And also reduce the waste. So there are a lot of research on vertical and also horizontal wind turbines because this can be installed on the rooftop of the buildings because they introduce less vibrations and also can help into the generations of the power. So this is, I think, very common. I'm not going to go to this because let me talk to this. This is the most important slide in the presentation. So what this slide means, this is actually extracted from a journal, Science, one of the top journals in the world, Science, impact factor around, I think, 50. If you publish one paper in our university, they give you $100,000. Nature and Science. These are the two journals, Unfortunately, for electrical engineers, impossible to publish. Most of people publish in this is physics, chemistry, medicine. Electrical engineer will never, unless they will change. So we will never get $100,000, no problem. So we will never get it. So what's this slides actually? It's an important slide, which is, this is actually studying the impacts, the generation and the emission. Okay, if we continue, as we said just now, the world population increases, right? If the world population increases, the demand for energy will increase. If we continue the same, what will happen? Emission will increase. That's it. Very, very direct relationship. There is no maths behind it. There is no equations. Very simple equation. Increase the generation, emission increase. So what will happen? So the energy, if we continue, the emission will increase linearly, or may have different shapes, depends on the interventions of the government, but it may go this. Let's think, or let's decide, if we decide to stop the emission, but continue the generation. This is the biggest question that we have to answer. Means, if we continue the generation, because the demand is there, but we stabilize the emission. Is that clear? Generation continue to increase, but emission stabilized. What we have to do? We have to, what you call, have this stabilization triangle. Stabilization triangle means you stabilize the emission at a certain point or certain level. Depends if you consider the 2010 level or 2020, 22 or 2003, depends, then you have this triangle changing the shape. All right? So this is what you call stabilization triangle. Okay? So what we have to do if we want to achieve this? If we want to achieve stabilization of emissions, we need to install 1,000,002 megawatt wind turbines. Why? Because wind turbines will generate electricity and with less emissions. Makes sense, right? Generation increases, emission maintains. What else? We need to install around 3,000 gigawatt peak solar power plants. Yeah, because what we said we want to stabilize the emission. That's the only way. Next, install 700 gigawatts of nuclear power plant. This was yesterday's discussion, Now Europe already classify nuclear as green energy. Yeah, Europe is already classified. Nuclear is green to get the carbon credits. And the one behind it is the French, because France, 60% of electricity generation in France is from nuclear. So the world rules changes, depends on the interests. You can see, yeah, it changes. Now nuclear is a clean technology and classified as a green. A few years back, it was not allowed. Many countries try to do, but not allowed. It's dangerous. It's harmful. It's not green, So that's what we, unfortunately, that's what we're living. So, but from an engineering perspective, we believe nuclear energy is an important component in the energy mix. We don't talk about politics. We are not politicians. But nuclear is an important component in the energy mix, because I think it's have achieved a certain level of efficiency, certain level of safety. Also, it's one of safest. I know there is people, whenever we talk about renewable, we always remember the Fukushima nuclear disaster, Chernobyl disaster. But, I always give this example. Nuclear is similar to airplane. The safest mode of transport is airplane. The most dangerous way of transport is walking. People walk, many accidents during walking, and motorcycles, bikes. That's the most dangerous, because you know how many people dies walking and how many people dies in airplanes. But when one airplane fall, everyone in the world knows that is in Venezuela or whatever, everyone in the world knows that this airplane fall and 100 people die. But how many people dies driving cars every day? Maybe 100 times of that number. Same thing happened to the analogy of nuclear. When there is one nuclear in the last 100 years, oh. But how many people dies because of the carbon that we always, inhale from the coal power plants or from the gas turbines? It's more and more and more than that. So that's, but it's one of, so nuclear power plants, so this is an important one. Oh, sorry. And then what we have to increase, this is an important also, increase the fuel economy of the 2 billion cars from 30 to 60 miles per gallon. Means the current cars that we use, IC engine, the internal combustion engines, are not efficient. For example, if you put 1 liter, it takes you 10 kilometers. This engine needs to be improved to take you 20 kilometers, improve the efficiency. But this it will never happen. Because in the last 60 years we're using the car, we never improved the efficiency of the internal combustion engine, Still at the same level. In the 60s, maybe improve, maybe 5 to 10% today, nothing else. But maybe there is solution. We will see the solution later. Oh, sorry. Carbon emissions, this is also very important. Carbon emissions from buildings, 25%. There's a lot of constructions, there's a lot of emissions. Okay? And then also we need to introduce what we call carbon capture. This is an important aspect in trying to minimize the amount of carbon. So carbon capture is now a very important aspect, and we have to introduce this 800 gigawatts, especially for the coal power plants. Okay? And I always give this analogy because usually one nuclear power plant, the size of one nuclear power plant is around 900 to 1,000 megawatts. So it's 1 gigawatt. So 800 gigawatts equivalent to 800 nuclear power plants. Because the international size of any nuclear power plant is around 1 gigawatt. All right? So just to, so the question is, my question is, can we do this? Anyone want to try? Can we do this to achieve the stabilization triangle? So different? Can we do it? So if we want to achieve this, the stabilization, there is no politics behind it. It's just only numbers. We engineers, we always know 0 and 1, right? It's either black or white. There is no gray. So can we do this as an engineers? Yes. Who say yes just now? Yes, yes. When we look into the numbers here, 300 times. Anyone knows what is the Saudi, do you have wind turbines in Saudi, right? Yes. Anyone knows what is the size of the installed capacity of wind?
Almost 300 megawatts.
Okay, 300 megawatts. My question is, can Saudi make 300 megawatts multiplied by 300?
So
if Saudi cannot make it, no one in the world can make it. That's the fact. Because to do this, these economical factors, there's a lot of money behind it. If Saudi cannot do it, we expect what you call Somalia or to do it? No way. There is a technical capability, there is technological capability, economical capability. From the numbers, it's impossible to be done, even by Germany or even in the United States. Let's talk about the superpower, the so-called superpower. Can they make it? Impossible. It takes them maybe 30 years to reach to the current capacity. How they can make it 300? It's impossible. So looking into the numbers, it's impossible to do it. So what does this mean? Forget about stabilization, the emission. That's the question. That's the answer. Okay, so what I'm going to answer now, how power electronics can help achieving this goal without doing all of this. Okay? So I have to go fast. So let's look into our energy supply system. If we look into our energy supply system, you look into this. This is important. You look into this is the line. This is separating this is the source. This is the load. What you can see, one very common color, the dark blue, right? This one. So these are all power electronics. When you go and buy the fridge, we tell you this is an inverter-based fridge. What does it mean inverter-based? It means more efficient, but bit more expensive. When you buy air conditioning, they tell you this is an inverter-based. When you buy a washing machine, they tell you this is an inverter-based washing machine. When you buy a TV, they tell you this is an LED TV. What does it mean LED? It's a power electronics. When you buy a car, they tell you this is an EV car. What is EV car? It's power electronics. The heart of the EV car is power electronics, the inverter and the converters. When you go and buy light, tell you this is an LED. What is LED? An LED driver. It needs an LED driver to work. Means it's a power electronics. So on the load side, all our loads are becoming dependent on power electronics. On the generation side, also we can see, for example, storage, solar, wind, fuel cell, also needs a power electronics. So if we make improvement of efficiency, let me tell you, we will give an examples later, if we have time. So if we, for example, let's take light, as an example, light bulbs. Do you know how many light bulbs in the world? Anyone can guess? We have 9 billion. Let's go trillions, because many people does not know trillion. What does it mean? Let's make it simple. You know, we are 9 billion people, right? 9 billion people in the world. Let's assume for every people there is 2 light bulbs, so we're talking about 20 billion bulbs. Huh? Yeah, I know. We don't count this. I think there's 100 bulbs here. We don't talk shopping malls. We don't talk street lights. We don't talk about offices. We don't talk about many places. Let's say 20 billion. If we switch to LED, you know how much watt you can save? Multiply that by 20 billion. That's the amount of saving you can make. We will see it after this, okay? Can you put okay, so, this one I have to use this. All right, so, okay, even for interfacing between the grid, the sources, we always need this power electronics grid interface, either from wind or from solar or from, what do you call it? So, the connections, whenever you have the connections between different systems, like for example between UK and France, where they have the transmission, DC transmission on between them. So you need a converter on the UK side, you need a converter on the French side to do this. So the power electronics is required for DC transmissions. And this is also happens, for example, if you look into the China, the Three Gorges Dam, the largest dam in the world, 18 gigawatts of power. I have visited that place. This place is called Yichang City. Yichang, it's in the middle of China. This place called Dam City. Dam City, because this area is used to be a flooded area. So what they did to solve the problem of flood, they built dams. So there are mini dams. That's why they call it Dam City. And the power they generate there is not needed because that's a small area. They do need the power. The power is needed in Shanghai, in Hong Kong, in Beijing, Shenzhen, and so on. So what they did? DC transmission. High voltage DC transmission. And they need the converters on both sides to do this. So power electronics, it's an important component in here. Okay. Storage also, we have storage, different types of storage. Like yesterday we listened to Haytham and also Said talking about this. So in order for you to use this storage, you need a lot of converters that is power electronics dependent. Okay, I have to move a bit fast. For power quality improvement, we always use the STATCOMs, which are power electronics devices to enhance the capability of the transmission lines. Okay, what else? Okay, let's look into this slide. So the current world energy consumption, this is the current world energy consumption. we use almost 40% of the energy consumption is electric. So the rest 60% is non-electric. Okay? The total, out of the total energy we use only 40% is electric. Yeah, because if you look into the 4 industrial sectors, for example, industries, commercial, domestic, and transportation. Transportation is 98% still depend on the fossil fuel. All right? So 60%. In 2012, just to give you an example, we consume what is equivalent to 20,000 trillion watt of energy from 20,000 trillion watt. Today, last year, I think it was almost 30,000 trillion watt hours of electricity. So let me give you an example. What does mean what this 1 trillion watt hour? Give you an example here. One nuclear power plant of 1 gigawatt, one nuclear power plant generates around 7 trillion watt hour of electricity per year. Okay, if you have one nuclear power plant, it can give you 7 trillion watt of electricity in 1 year. So what does mean this 20 trillion watt hours? So if you do a simple math equations, actually this is equivalent to almost 3,000. You divide this by this, you get almost around 3,000 nuclear power plants. So in 2012, we consume what is equivalent or what is generated by 3,000 nuclear power plants. This is to see the amount of electricity that we have consumed. All right? Let's look into this 40%. Okay, the 40% just now, this 40%. Yeah, I'm going to zoom into this 40%. Okay, we zoom in it and see what is inside. If we zoom in that 40%, we found almost that from 60% from the 40% is motor drive. And this is very clear because most of electricity consumed actually is industries. Large motors, large machines. 60% is all in the, what I call industry. So 60% is motor drives. Lights, very important component. IT, when we're talking about IT, we're talking about laptop chargers, phone chargers, we're talking about data centers, and so on and so forth. It's a number. And also others like home, like different types of appliances. So if we make 1% efficiency improvement, we can save almost 160 trillion. 1% improvement. 1%, I'm not talking about 10%. I'm talking about 1%. If a device that is 90, let's make it 91% efficiency improvement. Okay? So we can save almost what is produced by 23 nuclear power plants of electricity. Okay, let's look into, I think I have to move. So if you look into our current system, our current supply system, we have this very complex figure. So we have a grid, solar, wind, storage, electric vehicles. So what do we do? Solar, we need the DC-DC converter, we need an inverter, and then we connect to the grid. Right? When we have wind, we have a rectifier, and then we have an inverter, and then we connect to the grid. Storage, the same. See, 2 conversion stages. 2. If I don't know you know power electronics or not, what is the efficiency of these converters? 100%. Huh? 100%. There is nothing called 100% efficiency. I don't know, I have not met this yet. But does not exist 100%. Let's assume it is 99%. We don't make him, let's say assume 99% efficient. And it does not exist. You know why? Because the converters, they have what they call efficiency curve. There is no, when you buy an inverter, they tell you this is inverter 99%. It's wrong. Because actually, it has one operating point, it is at 99%. Actually, it has a curve that ranges from 0 to 99%. If one example, if the converter is 10 kilowatts, so they tell you the efficiency is 99. That is actually maybe around 80 to 90% of its capacity if you operate it. But if you operate it at 20% of its capacity, the efficiency will drop to 20%. So if you average it, maybe actually you are operating around 60 to 70% efficiency in the best case scenario. But let's see, this is our friend here, says 90, we take 99%. Let's take 99% as an example. And if we use this power, we go back to the grid, right? And then we use this power, the load, like the example just now. So also we need this. All this, we need the rectifiers, we need the converters. So conversion here, conversion here. So what will happen if we make this change? We move to DC nanogrids. So we eliminate one conversion stage here. Right? We save 1%. Let's see our friends here. We save 1%. But actually we save more than 20%. And then multiply it by all. We remove this, we remove this. So, because the loads, all of them can do DC, directly DC. So we have no problem. So we can save a lot of energy in this. Let's look into IT. I think the IT is an important. It's expected 1% efficiency in IT equipment. We can save almost 20 trillion watt hour of electricity. And we see this very important now. Data centers, and this data centers requires a power supply that is 100% available all the time. Because like you see, imagine that you are a bank, or you are using Google, or using Tencent, or Amazon, or Microsoft. One minute blackout, it costs them millions of dollars. So when they design the system, they ensure that this is 100% availability all the time. It's become more critical. So, now, yeah, I'm going to talk about this. This is the microprocessor. I don't know you know this about or not. So the microprocessor in the, I don't know, you know the 4004? We used to have it in the 70s, the 4-bit microprocessor. Yeah, so I don't know, most of you are very young, they don't know this, and then we moved to 886, 286, 386, 486, Pentium 1, Pentium 2, and then I lost track. I don't know what's now, what we have. We have i9, i7, whatever, So what does this mean actually? The integration level, the number of transistors in single chip is keep increasing from few to millions. We're talking about 6 million transistors. All this requires power, right? So this is from the integration level. So we move from the 486, and then we reach what we call the power wall. The heat dissipation become a very big issue. If you look into this 4-core processor, actually most of the time all the cores are in the sleep mode. The only one doing work is one processor, maybe one main processor. And then if we zoom in, we see actually even this one core actually is operating sometime, and the power, how the power supply. If we change, this is just the integration level actually. We already have in the market the E7, the 15 core. Very soon we'll have the 200 core processors. But the big issue is the heat dissipation, because as you know, the semiconductor, the enemy of semiconductors is the heat. The moment you cannot control the heat, you cannot control the operation of any semiconductor. So heat dissipation is a major issue. Let me, I think I have to escape this because, yeah, I will look into this. So this is the processors, So this is how the power is supplied, the per core, what I call voltage. This is the conventional way how we supply. It's almost a constant, supply power to the processor. Either they are working or they are not working. This is how we supply. So if we do what we call dynamic scaling, means you supply the power as you need and increase the frequency and reduce the voltage, we can save between 40 to 60% of energy that is supplied to the processors. And as I said just now, from a personal perspective, it does not look much because 70 watts laptop, very cheap. But multiply that by how many processors around the world. You can see the impact that we can make. So we can save between 40 to 60%. That is huge. Okay, I think, yeah, I give you this example actually. This is a very common example for power electronics, the impact. So this is actually the power supply for our laptops, right? Usually we have between 8 to 18 volt supply. And then it goes to the laptop. We have different devices. We have the LCD display, the power, the CPU. They require different voltages. So we use the voltage regulators, right? Okay, So this is the traditional way. This is, I don't know, you know this power electronics or not. So a simple topology, hard switching converters to do this, and then we modify this. This is modified by researchers where we introduce what we call soft switching. So we don't switch at any voltage or any current. We switch at 0 voltage and 0 current. So to reduce the losses. So I want to show you the impact of this. See the impact. Improve the efficiency from maximum 85% to 95%. Just by adding small inductors and small capacitors in the converter that we use. So multiply that by how many charges we have, how many phone charges, how many laptop charges we have. You see the amount, 10% efficiency. 10% efficiency, it's a huge amount of saving. So this is almost equivalent to what is generated by 60 nuclear power plants. You can see how power electronics can help to reduce the energy consumptions of these small devices. Yeah, I think the data for what we call data centers. Now most of them using the AC data centers. The big companies like Google already shifted to DC data centers. Okay, so no more these conversion stages. You know, these conversions in the UPS system, they reduce it. So now the biggest companies like Google already moved to DC data centers, removing all this conversion. When you remove this, you save 10%. All right, almost 5% improvement. Okay, I think I have to lights. Very simple. Lights. So if we switch from this bulb to this, we can save almost 20%, 20 times. Not 20%, 20 times. So what does that numbers mean? Almost what is generated by 450 nuclear power plants. That's the amount of saving. I know it's expensive to switch to LED, but if we do it gradually, that's the amount of saving that we know. And always I say, multiply by the number of bulbs you have. All right? Okay, this is the biggest brother, you know, the biggest guy, the 60%, the motor drives. Okay, let's assume that most of the motors that we have, they already have around 30%, the energy saving from using the VSD, variable speed drive, you can save up to 30%. And assume 40% of the motor drives already have VSD, means the existing one already have 40%, so we have only 60% to modify. Almost 300 nuclear power plants. So if you introduce the VSD in all the motor drives, that's the amount of saving that we have. That's why many countries now in Europe and many in US, you are not allowed to install low efficiency motors in industries. And they're giving a lot of incentives in what you call installing the VSDs and variable speed drive, because that saves a lot of energy. Okay. Okay, so yeah, appliances, I think we see this now. We are more electrifying our life. We see, I think, the train, which is one of the train becoming almost electric. Aeroplanes, there are more components moving from the mechanical and what you call hydraulic systems to what you call electric. For example, I give you an example: the 380 Airbus, what you call doors now are driven by power electronics. They are no more using hydraulic anymore. We see the electric cars, the industries. I think that's very. So let's look into this back. The picture. You remember the 4060? The 4060? If we do one switch, which is this, switching the 40 become a non-electric, the 60 become electric, we can save almost what is generated by 1,000 nuclear power plants. So if we shift, we call it electrification. Means, what does mean electrification? I think I have an example after this. Let me go to the example. I will give you an example. Yeah, this example. This example. This is what we call the impact of electrification. If we have the normal IC engine cars, the internal combustion engine cars, so we have the oil or petrol that we use, we generate and then transport. Every car goes around 670 miles per barrel of oil. So if you use 1 barrel of oil, it takes you almost 700 miles. Okay? This is based on the current efficiency of internal combustion engines. If we don't do any change, the source is still the same, it's the oil and gas. But instead of using that, we use EV. The source, as I said, is the same. This is what we call electrification. So we can go 1,100 miles. So that is equivalent to 65% efficiency improvement. And if we replace this source by wind or solar, you can see the amount of saving. So this is the impact of electrification. Sometimes even the source, I know many people say, yes, why we use electric cars? Because the source is still using coal and oil. Yeah, it actually has a lot of impact on energy saving. And to tell you this is actually this slide. Maybe I have to stop to give some questions. So this is the to share with you. In all countries, they have what you call energy flow diagram. Every country have what you call energy flow diagram. This is the United States. I got it from the Department of Energy. So this is the United States energy flow diagram in 2009. So what they have? 40%, almost 40% is electric, 60% is a non-electric. Which is matches with the pie just now. Remember the pie just now? The pie chart, 40-60. United States, this is their energy flow. This is the input, this is the output, where it goes. What's their plan? This is their plan. The plan is to move 80% electric, 20% non-electric. So actually means it's the world is moving towards electrifications. I think the recent announcement last week of the major electric manufacturers in US, the Ford and the biggest companies in US, the manufacturers, they're already starting building plant to build cheaper electric cars. Not only Tesla. Tesla is very expensive, but now they are a big mass for moving to electrification. So this is actually the trend. All right? Okay, I think I have to end somewhere here. I'm not going to talk about these smart grids and smart homes, So this is the power electronics. I would like to open for questions or comments. Okay, so I think that's maybe there are a few slides I don't want to skip. I think time is out, so maybe you can give a couple of comments or questions. Please feel free. Thank you. Okay. Francisco.
Well, it's time for questions. If any one of you have a very specific question, let me go there.
Hello, Dr. Saad. Thank you so much for the informative and inspiring presentation. Actually, I guess this is one beside Dr. Haytham and Dr. Saeed yesterday was a very good presentation about the energy and the energy trends for the future. This is Abdelaziz Al-Malak. I'm an assistant professor at the College of Engineering, the Department of Electrical Engineering, and the supervisor of energy efficiency unit at the university. And I lecture electrical energy efficiency and also energy efficiency. So I found this topic very interesting and very good topic for the students. My question here, and I would like to comment about the 100% efficiency. I 100% agree with you. There is nothing to be 100% efficiency unless if we have DC-DC system that would mainly convert the energy from the DC components to other load components. So I would like to go to slide 31, if you can go
Yes,
to it.
sure.
Thanks.
Can you put the slide, please?
Yes, here. I think in this slide you represented the overall system that based on the generation side and the transmission side, then the load side. And basically in this presentation you describe the load side, how they are dependent on the power electronics. My question here, how about the generation sides? We know that the generation or the traditional generation is about from 32 up to 40% efficiency. How did the power electronic contributed to the solution in this generation? And also in regard of the renewables in overall. Thank you.
Thank you. Thank you very much for the comment and also for the question. So what we can see, what my objective of putting this slide actually is showing that our loads are becoming more dependent on power electronics. That's the message I say. The message is the loads are moving from the traditional loads to power electronics driven loads. Also on the generation side, remember just now what we shown, the wind turbines. So wind turbines, 100% of their power is already processed through power electronics converters. So what you can see now, the generation, on the generation side, there is an increase of renewables. So there is an increase on the use of power electronics in terms of, for example, solar, wind. You can see the thermal. It can actually, the power electronics can be used in this kind, even like now the movement into the green hydrogen. When we move to hydrogen storage, for example, as one of the source, power electronics becoming an important component in hydrogen. You cannot use a hydrogen without a fuel cell, and the fuel cell you need a converter. So that's actually the power electronics. So what the message here is, the future will be more of power electronics. Means every thing that we do either on the generation side or on the load side will be a power electronics. Even the transformers, we are moving to solid state transformers. You know, that's the facts, you know, so that's how it's moving, and it takes some time. Like what we see the loads here, it takes some time, it takes some years to reach to this level, but the future will be for more power electronics driven loads and also on the generation. Thank you. Yeah, please.
Assalamu alaikum. Thank you, Prof. Saad, for this fabulous presentation. This is Fuhaid al-Shammari. I'm an assistant professor in the Mechanical Engineering Department, and I'm teaching courses related to thermofluid area. But when I start talking to my students, I find myself digressing on the issues of renewable energy and such. So since I see some of my students here, I will start and end by this basic question, which consists of two parts, actually. The first part, why is the world waiting that long to commercialize this renewable energy technology? And the second part is it possible to get rid of fossil fuel completely, let's say in the next century? Thank you so much.
Thank you very much. I think very, very important and very interesting question, you know. Why the world takes so long to reach to this level? You know, technologies, as a researchers, what we do when we do research and then we either we patent it and we publish it and we move. In order for these patents and this to be in the market, it will take some time. It takes some time because there are many factors. First one, I give you an example. This semiconductor. Why this now we have more loads, dependent on inverters. This was not possible 20 years ago. Why? Because the cost of the semiconductor was very expensive. The controllers we use very expensive controllers. Now there is the controller, 5 riyal, 10 riyal, you can get a microchip controller which can control the inverter. Very cheap cost. But before this was not possible. So the advances in the control on the processor design and the costing also dropped significantly on the semiconductors. That leads to this, to the more introduction. Because, the market, you cannot control the market because the cost actually is driven by the market. The bigger the size, the market, the lower costs that we can have. So we have reached to that level now. We have reached to the level where the cost of introducing inverters in all these loads will have a minimal impact on the total cost of the system. And also, people can see, okay, for example, if I use an inverter-based aircon, okay, I take it for 5 years or 3 years, the payback time has reduced from 7 years to 2 years. So this is a good investment for people. So every technology will take some time to mature. Solar cells, I showed the slide just now. In the 70s, the cost per watt was $75. Today, 20 cents. Why? Because investors, business people, come invest in the technology, and that helps to reduce the cost. So every technology will take some time to mature, to reach to the commercially viable technology. And I think for all these types of loads, we have reached that level. And on the generation side also, now the break-even point between the electricity generated from solar and wind is similar to the one generated by gas. They already have the same price level. Okay, so this is actually my questions, my answers. Will be in the future, can we get rid of fossil fuel? This was one of the students yesterday, Saudi student asked me this question, Will one day we don't need fossil fuel? In my opinion, we will never reach the day. We will always depend on fossil fuel. What we believe, if we reach a balanced energy mix, let's assume, for example, in Saudi, we depend on 80% on gas. Can we reduce the dependency on gas from 80% to 30%? And what will happen? The reserves of gas will last longer. So your grandchildren will have access to this and benefit from it. Actually, we are not going to get rid because there are a lot of industries, a lot of things we cannot convert in one day. It takes hundreds of years to convert. To move from an IC engine, how long it takes us? It's more than 100 years. To move to electric, and we're still not yet fully electric. And maybe the current engines will last for another 100 years. So to get rid of fossil fuel, it's impossible. It's not possible, but the dependency on one source is not going to be there. So it will be what you call increasing the energy mix. So part of renewables, part from gas, part from coal, part from different sources. So that actually creates a more energy secure supply system. Thank you. Yeah, please.
Assalamu alaikum. Thank you, Doctor, for this very interesting topic in the energy consumption. This is Dr. Khalid Al-Gunun, Associate Professor of the Electrical Engineering. We have talked about the energy consumption and the energy saving by changing or providing power electronics.
Yep.
And by providing efficient inverters, efficient converters, whatever. However, could we reach the energy consumption by alternative ways, such as changing the behavior of the end user customers by providing various options for the end user customers, and how can we reach that level? Thank you.
Thank you very much. This is also very important. This is what you call the awareness, And I can give you an example of my wife, my wife, she's a lawyer, lawyer, woman and lawyer. So you will never win, And I am an engineer, I believe only in black and white, either on or off. To tell you the example, So, when I ask her to make for me a cup of coffee and tea, we have the kettle, she go and boil 2 liters of water, 1.8, exactly. I know the amount of water that you can put in the kettle, 1.8. She boiled 1.8, and we are only 2 of us. She makes maybe 100 ml for me, 100 ml for her, so the rest is 1.6 liters of water, boiled water, and left like that. Then I ask her, why you boil this all amount? You just put the minimum, which is 500 ml, the minimum, because there is a minimum level. No, why? What's the difference? She says. You are very stingy. You want to pay the electricity bill. No, it's not the money that matters. I tell her, if we use this is the amount of energy we save. This is the amount of energy. But she cannot believe in it. It takes me years, more than 20 years now. I'm trying to educate. I'm trying to play my role, because I have to apply it in my home before I teach it to my students. The same things. When we go, for example, for shopping, can we walk? No. Why do we have to walk? We have a car. So this is a way of life, as I say. Like we say, Islam is a way of life. You practice it. When you walk the Muslim way. When you work the Muslim way. That is the Islam. To practice the way how you live it. The same thing, energy. You have to live as you believe that actually every step that you make, it makes difference. That's why I say just now, there is no point of talking about renewables when we leave our lights and we put our air conditioning at 16 degrees and then we buy a jacket to keep us warm. There's no point, actually. It's just a waste of money. So awareness, education, it's a very important. And I think yesterday our colleagues, they talk about automation. And then that's what we see now. There's a lot of automation happening. For example, sensors, occupation sensors, in the cars last time. Now, when you put the car, when you stop in traffic light, the engine will turn off. That is energy saving, that's automation. So we can see the technology actually is helping to improve the energy efficiency and energy consumption per person. But as I say, it's our job as engineers and scientists to educate the public and to tell them actually, when you do this, this is the impact that you have to do. The awareness, So that's very, very important. And I tell you, your wife and my wife can make more difference than me and you, because she at home most of the time than us, So if she can save, for example, how many watts per day, multiplied by the number of wives in the household, then you can see the amount of saving that we can do. Thank you.
Thank you very much for your amazing presentation and insightful reflections. And I just want to make a comment. We are in a society that we are pressing for smartphones, smart cars, smart things. What we need is smart people, because at the end, changing the behavior of the customer is basically human behavior, and that is for smart people. Thank you very much for your presentation. I would like to request thank you. And I think this is the end for this session, and I don't know what to say. This is the end for this session, and somebody will take over the next session. Are you presenting me, or I can present myself? There's no problem. Well, welcome everyone. My name is Francisco González Longat. I am a full professor in University of Southeastern Norway, far away from here and colder than here, of course. And It's a pleasure for me being here. Thank you to the organizing committee for the invitation and all of you for sharing time with me. I do apologize because my presentation, okay? I will try to do my best and keep the time inside the schedule, and I will try to go as fast as I can, okay? Sorry if I jump some of the slides, because I believe I have a very limited time today. Okay, what is the topic? I think you took the pointer with you? Yes. No, the pointer, yeah. Could you hear me? Yes. Now let me switch off this one. Okay, initially I would like to say I'm sorry I'm not power electronic guy. Here there are people that know more about power electronic than myself. I am a power system guy. I mean, for me it's generation, transmission, distribution, and the customer, okay? However, in recent time, many of my colleagues already say power electronics is a very important component inside the system. And today what I will discuss is some of the challenges and some of the solution, okay? The good news is there are more solutions available over the time, and it will be more solutions even over the time. Let me try this. Oh, what I did? Oh, Jesus. Could you hear me over there with the presentation? Yes. And this is to move forward? No. Which one is to move forward? Yes, that is the one that I'm pressing.
Yeah, so this one?
Yeah? That is the last slide. Could you move at the very beginning?
Yeah, starting.
Yeah.
So this one here?
Yeah.
Is forward, this is backward.
Good.
The big one is forward.
Ouch. And this. I can see that my pocket is out and nobody tell me. You are really bad guys. And now it's not moving. Oh, yes. Yes. Well, this is commercial time. I will tell you about my lab. I am the leader of the DHENSYS lab. That is the short for Digital Energy System Lab. What we are trying to do over there, I say trying because we are trying, we never finish doing research. We are trying to integrate digital technologies in electrical power systems. That means including new communication system inside the power systems, using artificial intelligence and so on, okay? At the very end, I will show you some of the, let's say, some of the examples about what we are doing. Now, what is the context and motivation? Every time that I need to talk about power electronics, I use this very small photo over here. I believe some of you have seen this photo before. This is a photo of New York City, 1900s. That is the Fifth Avenue in New York City. And at that moment, the question is, where is the car? If you look over there are plenty of horse carriage, and there is a single car. Then somebody took the same photo, 1913. 13 years later, somebody took the same photo in the same place, even in the same Sunday of Easter, and now the question is, where is the horse carriage? As you can see, there is only one over there. And that is technology. Technology change. In this case, something appeared, internal combustion engine, that is a technological development, but it's also a market disruption, okay? Because this is something that was created by humans in order to solve problems of humans, transportation, okay? But the good question over here is, if you ask Henry Ford, why he created the car. Well, the motivation was trying to provide a new product inside the market, try to change the way that we are transporting. And there is a famous quote that say, somebody asked Henry Ford, why you did this? And he said, well, I want to improve the transportation, use the technology, and so on. But he said, if I heard the market, people want faster horses instead of a car. And he created the technology. Now, probably you are wondering why I'm talking about this. Let me change the image. Now, there is a photo of electrical system. Electrical system has been based on synchronous machine. And if you ask, where is the power converter? There is only one over there, if you can see here, yes? And that is the situation in many countries. In many countries, they still with a lot of synchronous machine producing electricity, a small renewable integration, a small size renewable energies like wind power, PV, and so on. But the future can be a bit different. And now, oops, it's not changing now. Come on. Yes. Now, this is the future. I don't know. Depend of the country that you are, or depending of the location that you are based around the world, the situation can be different. But where is the synchronous generator? And there is a single synchronous generator over there, okay? Yes, finally. Why I am presenting this couple of photos? Because we are in a transition. Electrical power systems are in a transition. We are moving from a very old paradigm for probably more than 100 years, using the classic synchronous generation, using the classic way to produce electricity, to something relatively new, using the renewables and so on. And when I say that there are some countries that they are near to this photo, that is a reality in Europe and especially in Australia, okay? Well, let me move forward. Why this is so slow? It was fast. Oh, that way. Okay. Yes, but, okay. We have been talking about this transition in electrical power system. The transition is we are trying to reach or reduce the emissions. And to be honest, some countries, they are already committed to reaching the zero net production, okay? If you look over here, let me use my two hands over here, you can see that there are different countries and different targets. For instance, Bhutan has already achieved the zero emissions over there, yes? As you can see, there are countries like United Kingdom. We are already committed for 2050. However, there are very specific cities inside the UK that they are committed for early transition, like Manchester 2038, Bristol 2030, and so on. It's impressive the pressure that we are having to reach those targets. And reaching those targets means, come on, this is killing me. What's happened? Is this button yes? Is that? No, now move faster. Yes. Now forward. Come on, this is killing me. Oh, yes. Finally, we got the slide. Well, there are many intelligent people around the world working in this transition. And one of the good news is that there are people already defining a path for this transition to reach zero net emissions. As you can see over there, the Institute of Energy is already defined a pathway. And one of the interesting targets that we need to see over here is we are talking about 1,020 gigawatts of solar power by 2030, and we are talking about like 70% of the whole generation using renewables by 2050. Let me see if this is changing. I don't know, this is, this is making me crazy. And where are we changing the electrical systems? We are changing almost everywhere. We are changing the way that we are producing electricity. We are including more renewables. We already talk about more PV, more wind power, but also the way that we are consuming the electricity is changing. We are moving from those passive customers into more active people that they are producing PV systems, using electricity and creating electricity using PV systems. But that is not the only way that we are changing the system. We are changing the way also that the customer is using the electricity with these new technologies. We are having electric vehicles, a battery with wheels. We are having heat pumps in some countries in order to create cooling systems. We are changing the way that we are using the electricity. My previous colleague talked about the inverters everywhere, inside the washing machine, inside the dryer, everywhere. But also battery energy storage. We are starting to have battery energy storage inside the houses, and that is a game changer. Because now we can produce electricity using this PV system, we can store, and we can use whatever we want, even for charging the electric vehicle, making a huge change inside the use of the network, okay? But also, we are changing the distribution. The distribution used to be a very passive component with power flow moving from the source to the customers, and right now, with those active customers, we can inject power into the grid. That is a huge change. We need to change the way that we are planning those grids, the way that we are using those grids, the way that we are protecting those grids. And in transmission system, another game changer. Now we are talking about utility scale size battery energy storage, and that is a huge change. Australia, UK, they already have huge batteries with several megawatts hour of energy storage, and that is creating a huge change in terms of the use of renewable. It's making up the possibility, the reality of increasing the penetration of this new variable generation coming from renewables. The interesting thing is, in some countries, the market is a driver, and the market is changing, and this market is including going down to the customer, making the customer more active actor inside the market, and that is also creating a huge change. And finally, the way that we are operating the system. The system used to be human-based, the system used to be controlled by humans, but now we are including so many new technologies, artificial intelligence and machine learning. They are creating new ways discovering new ways that we can operate the system. And that is happening right now, okay? Let me go to the challenge. Oh, Jesus. This is killing me. I will finish in 3 hours if this keeps going. Oh, yes, finally, yeah. Well, this is a big picture about the electrical system, okay? Now we are having a lot of renewables. Right now I am based in the UK also, and we have a lot of nuclear power plants, but also a lot of offshore wind power. We are talking about also battery energy storage here, a utility scale size, but also the huge change that is, the game changer that is also having electric vehicles. Electric vehicles is coming very hard. In Norway, we have, in the last 6 months, 9 of our 10 vehicle sales in Norway has been electric vehicles. Now we are start to having the annoying part of the electric vehicles. We are seeing going for queues in order to get charge your car, and that is the bad side of these electric vehicles. The infrastructure must grow at the same speed that is also increasing the market for the cars, okay? Well, let me try again, this one. Yes. Many people believe that the penetration of renewable is just something that is happening in the mentality of the researchers. That is something that we are just thinking about that will happen 100 years from now. And that is not true. The reality is that many places around the world, they already have a huge penetration of renewables. That is the case of Denmark, that is the case of Northern Ireland, that is the case of also for Portugal. But one of my favorite cases is Australia. Australia is a very interesting case because they are having a huge penetration of renewable and especially inverter-based generation. As you can see in this plot, it's quite interesting because you can see that for a very specific moment in 2020, 52% of the generation came from renewables based on inverter-based generation. And what does mean 52%? 52% means that more inverters were producing electricity than the classical synchronous generator. If you remember my photo, I was asking, where is the synchronous generator? Well, as you can see, the situation is that the number of synchronous generators at one very specific moment in Australia was a minority compared with the inverter-based generation. Okay, let me try this one. Yes! And now, what is happening is that we are in a transition that in some countries is faster than others. For instance, the case of Australia, they are having the experience of moving quite fast for this inverter-based generation penetration. And we need to change the way that we are thinking about the problem. I mean, for many years, we have been having those inverter generation coming into the electrical power system. And what we have been trying to do is basically make the power converter behave like a classical synchronous machine. And that is one of the final conclusions that I will show you here, that probably that is the reason that electrical engineers, we are grown, okay? Ouch. I will take 3 hours like this. Yes. And what is the problem? The problem is this. Finally. What is the problem? I told you about the case of Australia. Here, we were at the very beginning of the power utility industry, we were here, 100% of synchronous machine, Thomas Alva Edison and so on. But then we realized that power electronics start to be useful for PV integration, battery, and so on, and they start to take off. Now this is the location for Australia, 52% of inverter-based generation. But the tendency is going in this way. The number of inverter generation is increasing, and the number of synchronous machines is decreasing in the electrical power system. Yes! And what is the issue? Sorry that I am using animals, but that is the best way that I can illustrate my idea of the situation. We have the synchronous machine. The synchronous machine has been the horse for many years. I told you from the very beginning of the utility industry, that has been the synchronous machine. And then we have here the power converter. The situation is that we are disconnecting many synchronous generation for many reasons. For instance, in some of the nuclear power plants in Europe, we are reaching the final life years of that. We are disconnecting that thing, and we are including now offshore wind power. But they look similar, but they are not at all. One of my messages that I would like to transmit here is the synchronous machine is beautiful, it's simple, it's very easy to use. However, the power converter, we are trying to make the power converter behave like a synchronous machine. And that is where the problem starts to be. Oh, yes. The synchronous machine is extremely simple. One moving part, that is the rotor, the stator. But with the synchronous machine, we have so many good properties that we didn't realize. Because the synchronous machine has been for more than 100 years in the electrical power system. We didn't realize that they produce so many good services that we didn't take care of. In fact, some of those services we were complaining for many years. Short-circuit currents. With a synchronous machine, we can have a short-circuit current several times the rate currents. And we were complaining about that. But now, when we start to have those power converters, we have a limited capacity for short-circuit currents. And also, the synchronous machine has an amazing property, mechanical property, that is the inertia. This moving mass inside the rotor is storing energy, kinetic energy. And at the moment that we have a power imbalance, well, this kinetic energy tries to be released and go into the grid, trying to reestablish the balance. That is the inertia. That is another service that we granted for 100 years. And now in Australia, in the UK, and many other places, we are starting to think about, okay, what to do to solve that problem. What I'm trying to tell you is that the synchronous machine is extremely simple, also in terms of control. Two basic controllers, the AVR, automatic voltage regulator, the governor, and that's all. If you have some inter-area oscillation, probably you can have another controller, the power system stabilizer, that's all. But it's an extremely simple machine. However, when we go to the power converter, oh my goodness, the power converter, to be honest, we have a misconception about the power converter. I know that there are people that know more about power converter here than myself. Sorry if I am making something wrong. But for me, the power converter is the box. It's the device that is converting voltages and currents. But we have a primary energy resource. It can be a battery, it can be a PV system, it can be a wind power, a wind turbine, etc. For me, the power converter is basically the device. And when we start to install all those controllers is when the magic starts to happen. For me, the power controller is this. The power converter is here. And the magic is all those possible control loops that we can add over there to do the magic, to provide services to the grid. But providing services from one power converter is different to providing the services from one synchronous machine. For instance, the synchronous machine already have inertia. That is something natural. That is something that is coming from physics. And it's different in the converter, because in the converter you need sensors. You need digital signal processing in order to try to replicate something that is natural inside the synchronous machine. And that is where the problem starts to be. Because this measurement, this digital signal processing and so on require time. And the behavior will be never 100% like the synchronous machine. And also, the power converter have another issue, short-circuit currents. To be honest, those power converters, they are amazing, they are extremely fast, but they are very sensible in terms of currents. And that is another of the things, okay? Let me move over here. Yes. Well, what is the problem? The problem is not the integration of the power converters. The problem is that we are disconnecting synchronous machine. And disconnecting this synchronous machine, we are losing so many of the good services, natural characteristics provided by the synchronous machine. And then, it's my opinion, FGL, it's my opinion that we are not thinking properly about the basic properties that we can get or the amazing services that we can get from the power converter, okay? It's this way. Yeah! For instance, what are the basic problems that we are facing with this reduction of synchronous machine? Well, there are several problems. One of them is the fault levels, the short circuit capacity. Now the power converters, they are not producing enough short circuit currents, and also the duration of that is not the same as a synchronous machine. In a minute, I will show you some numbers, okay? Second problem, regulation, reactive power. The synchronous machine have a very amazing way to produce reactive power, very simple, straightforward, but now we need to enable that on the power converters. Finally, inertia. Rotating masses have kinetic energy that is natural in the synchronous machine. In the power converter, we need to try to solve that problem in another way. Okay? Okay. Yeah. Those are examples of short circuit currents, okay? You can see over here at the top, here we have the voltages. You can see over here the voltages before the faults, and over there you can see the short circuit currents. What is the amazing difference between the power converter and the synchronous machine, between the Zebra and the synchronous machine? Well, if you look over here during the fault, you can see how the short circuit current is reaching like 65 kiloamps. That is huge, but that is something that can happen in a synchronous machine. We have a copper over there that is able to dissipate the heat. It's something that is allowed by the synchronous machine to be overloaded. It's something that can happen, and we are not destroying essentially the synchronous machine. But now, yes, we have the Zebra. And one of the interesting messages here about power converters during short circuit events is that depends on the controller. Depending on how the controller is designed, the short circuit capacity can be 0, or it can be defined until the rate current. That is something that is extremely interesting, because if we limit the short circuit currents to the nominal current, how we can create the difference between working in a normal behavior or in a fault. And that is a huge problem. From the protection point of view, detection, location of faults start to be a huge problem with power converters, especially because the limited capacity. And, oh, Jesus, back. Yes. And believe it or not, that is something that is happening in the UK. In the UK, we are starting to have so much power converters inside the system that the short circuit contribution is reduced. And that is a huge problem, because it's not also the short circuit current for protection, for detecting the faults, for locating the faults. It's also because the short circuit current is related with power quality. It's related with many other functionality. The strength of the power system depends on this short circuit ratio. And that is happening in the UK, okay? Another thing that is important is how fast the voltage recover after the fault. When we have a fault, we have different controllers inside the power system. The closest to the generator is the AVR. After the fault, they start to recover the voltage. And to be honest, the synchronous machine has been doing this very well for many years. And this is one of the places that I will talk bad about the synchronous machine. The synchronous machine can act very fast, but is limited by the speed of the controller. But in this case, the power converter can do even faster and better, and that is something that we need to think about for the future, okay? Let me move forward here. Yes. You don't imagine the stress that I have with this. To be honest, I am nervous, not because I am speaking here. I am nervous that this keep working. Come on, keep working. Okay, what are the possible solutions when we are trying to reach a high penetration of power converters? Well, there are short-term solutions, and that is something that we have been doing for many years. Short-term solutions include changing the grid code. That is something that happened. For instance, in the UK, like 5 or 6 years ago, we start to have so much wind power that the frequency start to move so much. And when the frequency start to move so much, what was the solution? Well, let's open the frequency band in order that the system can behave with that frequency variation, okay? What is the other thing? Well, there are other things that we can do, like auxiliary services. For instance, the frequency starts to move so much, we create a very specific service. In the UK, we call that enhanced frequency response. That means that we can respond to the change of the frequency, providing more active power in less than 1 second. The technology available for that, flywheels, ultracapacitors, and battery energy storage. But what are the long-term solutions? Well, the long-term solutions, they are a bit different, a bit tricky. One of them is enable the converter to provide some response similar to the synchronous machine, that is the synthetic inertia. And the other one is a control, the control technique applied for the converter, and that is the grid forming control. I will try to focus a couple of my examples later regarding synthetic inertia and grid forming control. Yes. One of the mitigating ways that we have used around the world is we are installing so much converters, we are disconnecting the synchronous machine, the rotational inertia is reduced. One of the ways that we have trying to keep the lights on is monitoring and controlling the inertia levels. This is something that is happening in many places around the world. Australia is one of the countries that has been leading that, even ERCOT in the United States, okay? What is the idea? The idea is that we quantify the total rotational inertia in the system, and from there we define security levels. And if the inertia tries to go beyond that, you know that something wrong will happen in the system and you will not have the possibility of recovering for that. And that is basically this approach. There are three different methods to obtain the total system inertia. One of the basic and the oldest one is the unit commitment method. The unit commitment method is extremely simple. You know how many generators are connected to the grid, and if you know the inertia of each one of them, you can do a basic addition, a basic sum of all of them, and you know the system inertia. The second method that we have here, and now disappear, is the driven event. In this method, what we have is we have a huge disconnection of a massive generator. We look at the frequency, and using some data analytics or some method, mathematical method, we can obtain the total system inertia. And then we have the most recent method, and that is continuous signal. Continuous signal is basically we are injecting some small changes inside the system, looking into the frequency, see how the frequency responds, and from there we obtain the total inertia. For instance, this is the case of Australia. In Australia, they are already operating the system. After the famous blackout in 2016, I think it was in 2016, after that blackout, they realized that the level of inertia, they have a strong impact on the security. And what they did was very interesting. They defined an area and limit for the total system inertia, and if the inertia is below certain levels, they take some actions. What are the possible actions? Well, connecting more synchronous generator, however, that is expensive, or the other way is using battery energy storage to compensate the possible imbalance created by the sudden disconnection of one synchronous machine. Okay? Yes! Come on. I will not discuss this in detail, but something that we need to understand is that not all the converters are the same. There are different type of converters, and there are different type of controllers applied to the converters. And depending on the way that you model those converters and the control that you apply, there is a huge family of what we call power converters, okay? However, here I will tell you about two different types based on the voltage and frequency behavior. One of them is what we call the grid following converter, and that is the typical converter that you can find in the market. Almost 100% of the viable PV system and wind power plants, they use this controller. This controller is basically a controller that is following the AC signal coming from the grid. That is the reason for the name following, because they need a voltage signal that they attach in order to provide electricity to the grid. What is the good news of this? This is a technology that is already mature in the market. It's very simple. It has been working for many decades. However, now we are using another control technique, and that is the grid-forming converter. The grid-forming converter has many advantages that make a probably solution for the future. One of the advantages is the way that we control the converter. First, the converter behaves like a voltage source behind an impedance, and that is similar to the synchronous machine. If you look, the most basic model of the synchronous machine is the classic model, a voltage source behind impedance. For that reason, it's almost the same model or similar to the same model of the synchronous machine. And also, one interesting thing is the way that we are controlling enable the very easy implementation of frequency controllers. We are not using this PLL. I will not go in so many detail, but that is the device creating the attachment to the AC signal. And this device, of course, requires some settings, and also the dynamic behavior of this component is affecting the whole dynamic behavior of the whole system. Okay, let me move forward. Yes, let me jump is, ouch. What is the problem with grid-forming converters? Grid-forming converters, many people say that that can be the solution for the low inertia or the 100% converter system. However, one of the problems is there are many, many flavors. Many people like me publish papers. They try to be 100% originals. They modify just a beta controller. They publish a paper. There is a new way to create the grid forming. Over here in the next slide, if this thing change, it's a summary of some of the ways that we can create grid forming converters. There are people that they use the full model of the synchronous machine, and they try to replicate 100% one-to-one the model of the synchronous machine using just very control theory. But also, there are more recent and more different approaches to create those grid-forming converters. Let me move forward because I am taking so much time. Let me jump this, jump this, jump this. Yes. One of the things that we have been doing in the lab is trying to replicate the behavior, the frequency behavior of the synchronous machine. In this plot over here, you can see the frequency response of different sizes of synchronous machine. In this case, what you are looking over here is how the active power, the megawatts, change when you have a drop in the frequency. When the frequency drops, the machine tries to reestablish the balance and is releasing energy from the rotor, from the kinetic energy store over there. That is what we call the inertial response, okay? If you look over here, this is something natural happening in the synchronous machine. When the frequency is dropping, automatically the active power increases, and then when the frequency tries to stabilize, well, the contribution starts to reduce. What is the bad news regarding the inertial response? There is something bad regarding the inertial response. When the frequency is dropping, the machine is releasing energy, is producing power. Good, that is great, because it's trying to reestablish the balance. But there is a recharging area here. I don't know if you can see here in red color and the sad face. Because when we have the under-frequency event, yes, the machine is releasing kinetic energy, but remember, we need to keep the balance, the energy balance in the machine. And at that moment here, when the frequency starts to recover, well, the machine will try to get some energy from the system. That is the sad news coming from the inertial response. The synchronous machine is beautiful, but it's not perfect. Then, what we have been doing is creating controllers to try to replicate that. One of the first controllers that we did, it was a basic proportional differential controller. That is basically the inertial response. The inertial response is H multiplied by the FDT, that is the rock-off of the machine. We try to do that with battery energy storage. We published a couple papers regarding this. However, there is a huge problem when we are trying to replicate the behavior of the machine using the power converter. I don't know if you remember, but the active power of the synchronous machine increased, but we never reached this point over here, and this is happening in a power converter. A power converter has a maximum power that they can deliver, and if the rock-off and the gain of the controller is so high, the converter can reach the saturation area, and we will reach that point that is not happening in real life in a synchronous machine. What is the conclusion over here? We can try to make the converter behave like a synchronous machine, but the problem is you will never get 100% identical response, okay? Okay? Another problem with replicating the behavior of the synchronous machine is if the frequency change in a synchronous generator, the machine doesn't require any sensor or any signal processing. I'm going on that, no worries. But in real life with power converters, we need digital signal processing. And when we have digital signal processing, we have noise. And when we have noise, that is really bad for the controllers. One solution, well, including filters. But those filters, they create time delays inside the response, and they create another problems in another frequencies. That is one of the issues that we realize over here. Well, we propose something that is called fast active power injection. And what is the fast active power injection? Combining the inertial response from the classical synchronous machine, but also including the droop response. That means that we are including the differential control action, plus we are including the proportional control action. What was the good news? Let me jump. We were able to publish paper, yes, that is the job of the academics, publish papers, but also we demonstrate that we can use several energy storage devices in order to compensate frequency response. For instance, in this publication, we used 3 different assets. One of them was the ultracapacitor, the other one was the flywheel, and also the battery energy storage. And probably you are wondering why 3 different energy storage systems. And the reason is the energy density of each one of them, and also the response. Ultracapacitor flywheels, they tend to behave extremely fast, but the battery, they can cope with longer terms. And that was the reason. We published this paper using physics logic, and most recently we use reinforcement learning, okay? The good news is with using this kind of artificial intelligence, we were able to identify better solutions compared with the traditional control. I mean, if you use the proportional integral or proportional integral and differential, they have, okay, if you set up the parameters in a proper way, you can get a good solution. But those methods have the possibility of adapting over the time, and that is a very beautiful property. Finally, we are almost closing here. Well, if this allow me. I would like to tell you about some of very interesting things happening in the UK. We are concerned in the last 5 years, we have been extremely concerned about the disconnection of the synchronous machine. We are disconnecting so many very old power plants using gas or using even coal, and for that reason we are losing so much inertia and other services. UK is one of the first countries around the world to having this kind of services, and that is providing inertia. If you look over here, a contract for providing a very specific amount of inertia was signed by 5 different providers. And they are providing the inertia using the classical synchronous capacitor. If you remember, a synchronous capacitor is a synchronous machine, but it's not producing active power. It's only for producing reactive power and controlling the voltages. But in this case, in the UK, we are paying those capacitors not only to provide the reactive power, it's also to providing the service of inertia, because we already identify that we have some areas, especially in Scotland, that we have so much wind power where the inertia is extremely low, okay? Finally, sorry for this image. To be honest, it's grown. To be honest, it's grown, because it must be a zebra on top with the horse costume. But I didn't find an image like that. Why that is my conclusion? Because if we have a zebra and we put the costume of horse, what we are trying to do is using the converter like an identical synchronous machine, and that is unrealistic. I mean, for now has been the solution, for the next decade probably will be the solution, but my main message here is to give you the idea that the power converter is extremely fast, and we can start to do many other things that we are not doing now. If we think about very low inertia, 100% converters, why do we need to keep using the frequency as an indicator for the operation of the power system? Another thing, I don't know if you realize, but if we reduce the inertia so much, a very basic assumption about the circuit theory is no longer valid. If you remember, when we are studying AC circuits, we use phasors. And one of the reasons of the phasor is because we have a reference rotating at synchronous speed. And if the inertia is reduced so much, the concept of phasor starts to fail on this validity of this reference rotating at constant speed. For this reason, my conclusion here, my message over here is, we are evolving in the power system, but we need to think in another way that we are evolving and how to reach that final goal. My colleague over here, he proposed a very good way, and that is the human behavior and reduction and also the efficiency. But my message over here is, we need to think about the way that we are doing engineering in the future power system. We need to think about taking the advantages of the zebra and start to forget the horse, okay? And don't try to paint the horse on white. That is also not working, okay? If you have any question, to be honest, I will be extremely happy to answer. Yes, there is a question over there, yes. And finally, I finished the paint with this. Thank you. It was painful for me, sorry. I know for you it's not, but for me it's extremely painful, sorry. Thank you. No, at the bottom, the switch is at the bottom. Yes. Yes, we are delayed, yes, sorry. You can?
Okay, thank you very much.
Yeah.
Thank you, Professor, for this very interesting topic, very intensive presentation. You have mentioned actually the energy storage system as a game changer, which I think this is totally true. I totally agree with you. However, my question is, we have many challenges regarding the implementation of the energy storage system. We have the problems of the cycle life. We have the problems of the sizing and location of the energy storage system. You have mentioned also the frequency response. We have variation of the frequency responses. The lithium ion is not compared as the lead acid in terms of the frequency response. So my question is how to overcome all these challenges and make the energy storage system as a game changer. Thank you very much.
Thank you. Thank you. It's a very interesting question. And I will give you the very short answer because the boss is asking me to do this fast. But the answer is, there is no unique solution. For me, it's an integrated solution that you have a mix of different energy storage technologies. And what you need to be sure is that that mix provide the service what is needed and the service with the characteristic that is needed. That is basically what you need to do. For instance, when we combine the ultracapacitor, the flywheel, and the battery energy storage was to take very fast the ultracapacitor, start to fulfill the requirement to go in a very step slope, and then when the ultracapacitor is almost dying, you jump in with the flywheel and try to give moment for the battery to start to discharge. And then when you sum all the responses, you get the proper. And that is the way that we are doing the same inside the electrical power system. We have the nuclear power plants. They have not so much frequency regulation. We have gas turbines that they provide fast response. And that is the same. What we need to do is take the best of those technologies, each one of them, and fulfill the service. However, my deep message over here is that using those new technologies, we can offer other services that we didn't think about now. That is basically the message here. The message here is we need to take the advantages of those technologies, forget the synchronous machine or consider them, but they will not be the main actor inside the system. That is basically the message over here, yes. Any other question? No, there is an important question. Any idea? Come on. The very important question is, shall we go? You don't understand? No. Can we go? Yes, let's go. That is the important question. Thank you very much, everyone. Thank you very much.
Thank you so much, Prof. Francesco, for this plenary session. It's time for break. Thank you, audience. About 15 minutes, they will be back, inshallah.
Hello. Check, check, check. Okay, clear. This is okay. This is okay for me. I feel, yeah, I'll not.
Try that one. Stay there.
Okay.
open the first presentation? Sam? Can we open the first presentation? Okay, thank you.
Are we ready? Yes, here. Are we ready? Yes? 1 moment. Okay, 1 minute, and we will start, because we are in tight schedule. And I'm not using the clicker. Yes. Oh, Jesus. Oh, Jesus. Are we ready? Yes? Okay. Hello, everyone. Welcome back. And it's a pleasure to introduce the new session today. And we have an amazing presenter. We have a Dr. Stanley Johnson, and he is a senior reliability engineer, control system and instrumentation with Madin, Aluminium Company, Saudi Arabia. Before joining to Madin, he was with SABIC, Saudi Arabia, Invensys, India, and Karunya University, India. He resides in Saudi Arabia since December 2009. Stanley has earned the PhD in control system in 1998 and instrumentation and control engineer by profession, a project management professional, PMP, and certified functional safety expert, CFSE. He delivers academic and leadership lectures, conduct courses for societies and academic institutions, and guides master and PhD scholar. Stanley has over 15 years of industrial experience, successfully completed many international projects of commissioning and upgrading of the DCS and PLC for industries. He has conducted more than 5,000 hours of training for international customer in operation and maintenance. And he has visited business in Singapore, Malaysia, Thailand, Kuwait, Qatar, Emirates, Oman, Bahrain, and USA. Being a member of the Saudi Council of Engineers, International Society of Automation, Project Management Institute, he is actively participate and serve of professional community by volunteering in seminar trainings, programs, and lectures. And he will be talking today the framework for life cycle management of safety international systems in manufacturing facilities of large corporations. Well, it's my pleasure to present him, and the floor is all yours. Please try to keep track of the time, please. Thank you. Thank you.
Thank you, Professor Francisco. Dear professors, esteemed professors in the field of automation and power electronics, and scholars and students, I am very happy to stand before you in this conference, international conference of instrumentation and control and automatic diagnostics. The year 2022, after all this pandemic, I'm very happy to be with you. And since this is going to be more academic and my participants, those who are listening, are from academics, I would like to make it more academic oriented. Though I come from industry, I would make a point to make this presentation will be useful to you academically when you go to the industry. Can you go to the presentation, please? So this is going to be a workshop. In fact, I was trying to make some quiz and try to get a feedback out of it. But because of the time constraint, I may have to forego those things. So this is the introduction for the workshop. The topic is framework for life cycle management of safety instrumented system in manufacturing facilities of large corporations. So we are going to discuss about a framework which will be managing the asset or safety instrumented system for large corporations, maybe having many manufacturing units. Like for example, I was working in SABIC. So in SABIC, we were having many manufacturing facilities. In Jubail itself, we have some 10 facilities, different locations. And in Yambu, we have, internationally we have. So the same work can be used in the other units, this framework which we are going to discuss about. Okay. I was also now I am with Madin, and in Madin also we are trying to implement this framework. So maybe time permits, I will discuss some case studies in this one. Okay. So today's agenda will be like this. We will be studying, because we are talking about the safety instrumented system, it is going to be, we will give a basic process control, how we do basic process control in industry. My part of the presentation will be basic process control. You will understand how we use the automatic control systems like DCS and PLC to automate this process and provide the safety, and how the final element is one of the important in industry to provide the process control or the safety. So we'll briefly discuss about the valves, control valves. Then we will discuss about the SIS. SIS means safety instrumented system. Safety instrumented system, how it is designed, how the reliability is established in that, we are going to see that. Then we will see the framework of reliability instrumented system, which is the topic which I have proposed to disseminate to each one of you. So it will be the RIS framework we will discuss, and finally a case study, how this is implemented in industry, in SABIC especially. Why this is important? Why a framework is needed for managing the safety instrumented system? So the safety instrumented system basically is used for providing safety. That means we are having manufacturing industries where the chemical process is going on, and if the process goes beyond control, what will happen? It will be a havoc. It will be a catastrophe. So to avoid that, we are having interlocks. And these interlocks are built into the safety instrumented system. Okay, it can fail, just like, you know, in our home, we are having fire alarms, isn't it? Do we have fire alarms in our home? Is it working? Many times what happens, it will fail in a different way. Okay, suddenly you will get an alarm. There is no fire, still you will get an alarm. Okay? So if the system really fail, it will not detect fire, and if real case of fire, there may be a big havoc. Okay? It's about that. But sometimes what happens, it spuriously fail and gives nuisance. In the middle of the night, you will get a fire alarm, there is no fire. In industry also it happens. So this is also a failure of safety system, isn't it? You agree with me? A safety system can fail dangerously, or it can fail in a nuisance. It gives a nuisance. So many cases what they do, they shut off the system and they go without a fire and gas system or alarms. Okay, it happens. Okay. So in order to avoid this, in industry, we are having a management system so that we can avoid the dangerous failure. If any fire or any dangerous situation happens, system should work. And in the meantime, it should not reduce the production. It should not make the company lose production because of the spurious loss, spurious tripping, nuisance tripping. Okay. So the standard which is being followed is IEC 61508. So this is a standard, and this standard is a universal standard for all kind of safety system. It is not only for the process industry or machinery, it is applicable for nuclear, it is applicable for railway, and various, you can think about anything, everything, it is coming under the safety system management. Okay? And this is widely used universally. From Australia to US, UK, they use this standard. Okay. Our framework is based on this standard, but IEC 61508 encompasses various industries and systems. So we have a substandard, we have a standard below that, is called the IEC 61511. Okay? So this is a risk management. In a risk management, what we do, in a general risk management, what we do, we identify the risk, then we analyze the risk, and give the mitigation recommendation, mitigate prevention or mitigation. Right? This is a risk management, generally. So the same thing we do in a reliability instrumented system. Okay? So we identify the risk, we identify the functions which will provide the safety from those risks. Then we do the verification whether this function, whatever we are maintaining, is providing the safety, whether the integrity level is good enough. We also then continuously monitor and improve this to be in place. Okay. Sam, can we go to the next presentation? So we have a series of presentation. So I'm thinking of giving a break after the third one, and the fifth one, and the last one. We will see. If required any time, you can interrupt me and we can have a break. Is it okay with you? Okay. Sam, can we go to the next presentation? Yeah. So this is pure academic presentation. What is process control? Because I'm seeing my audience is a wide range. So chemical, electrical, and all sort of specialization people are sitting here. So briefly, I will give introduction about the process control, then how we implement process control in the industry, and controls, the control valve. So these are going to be in this one, okay? So what is the basic process control, and what is DCS and PLC, control valves, SIS, safety instrument system design, reliability instrument system, RIS, how to do this workshop. So these things we are going to see, okay? Effect of loss of control, okay? So if we lose control, what will happen? There will be a big havoc, okay? You can see a runaway process goes out of control, a nuclear or chemical reaction will create a fire or explosion. Or a company like Bhopal, the cyanide, the gas like cyanide gas goes out, it will be, community is in hazard, fatality for the community. In Jubail, we are having a company, same company, in Bhopal in the year 1985, there was a big havoc and a whole community around that plant, they had fatality because it is a cyanide and the gas leaked and it goes to the residents. Same kind of company industry we are having in Jubail, but after that we have learned many lessons. We have implemented many safety instrumented system and we are able to manage that. But if it fails, it's going to be a havoc. Okay. We are trying to understand what is a control system. Okay. See, what you see here is a control system, a process control. Here, what we are doing is, we are trying to maintain the temperature of the chemical by circulating steam. So in order to do that, we are having, technically speaking, we have many variables. We have a controlled variable, which is the temperature which we are controlling. We are having a manipulated variable, which is the flow of steam. We call it manipulated variable. We manipulate it and we control the temperature. Then we are having load variable, because if everything is constant, no need for a control. Okay, everything is normal, you can keep the wall at constant, but the inflow temperature may vary, the quantity of flow may vary, so there is a load variable. Okay. If a human being is sitting and controlling, what he will do in order to control the temperature of the material inside, he will see the temperature and he will open or close the valves, isn't it? Right? The same thing is done automatically by control system. Okay. We are having controller which will be controlling, which will take the information from the sensor. Okay. And it will give an output to the final control element. Can you see the second block? There's a final control element. And the final control element may be a control valve or motor or something, which will actuate and it will increase or decrease the manipulated variable and it will control the process. Again, it is sensed by the measurement element and signal is going to the controller. So here, the controller, what we are talking about is the DCS or PLC. DCS means distributed control system, which comprises many controllers. PLC means programmable logic controller. Okay. So you can see there are many different sensors used in the industry. We are having sensors for measuring the temperature, pressure, flow, and so on. We have many sensors. These are sensors which are called the transducers, converting one parameter into another. Okay? This is a transmitter. Transmitter is a sensor connected to another unit which converts the signal into 4 to 20 milliamp or a voltage or a digital signal which can be read by the controller. Okay, this is a transmitter. You have indicators. In the field, you have indicators, digital indicators, analog indicators like pressure gauge. These are all in the process control of an industry. Okay, you have recorders. In olden times, we were having chart recorders, but now we are having historians or the database where the information of the process will be recorded. We have controllers. When I started my career, we were having single controller, and in a plant there will be like thousands of controllers, and a control room may be a very large room with full of controllers. But now these controllers are replaced by computers, or we call it distributed control system, DCS. We have final control element. The final control element is the one which is actuating the process or manipulating the process variable which we need to use for control. It can be a valve, it can be a motor, it can be a levers of the opening of the manifold for a boiler, or it can be a solenoid valve. So these are all the final control elements. The signal which is actuating really in the field. In a closed loop control system, all of you must have studied about this. Okay? This block diagram is inevitable for process control. Okay? So you have a controller, you have the process, then you have feedback. Okay? This is called the closed loop control system, where you are having a controller, a process variable is measured and it is manipulated. Okay? You have another type of control system which is called the feed-forward control concept, where the process is measured in advance and it is manipulated. For example, here you can see the temperature of the process is measured and the valve is opened or closed. Okay. But in this case, what we are doing is we are measuring the temperature of the steam, because sometimes the steam is acting as a load and the flow may be constant temperature and constant flow. So you go for a feed-forward control system. So this is called a feed-forward control system, where you will take the information in advance, the variation in advance, load variable, and you are controlling. Okay. This is called a cascade control system, where you are having a master and slave control. Okay. Here the objective is to control the temperature. Okay. But in order to do it efficiently, what we are doing, we are accurately measuring the steam flow. We are measuring the steam flow, and you are having two controllers. You can see here, are you able to read FIC and TIC? Can you able to see from that? So you have two controllers, what you are seeing in the screen. Okay? So the temperature controller will give a set point to the flow controller, and the flow is measured in the flow of steam is measured and it is controlled accurately. So this is called this arrangement is called the cascade controller. Then you are having a ratio controller. You are trying to control the ratio of a process accurately. Okay? So you are measuring, one is called the wild flow, another one is called a controlled flow. So you control the controlled flow, and whenever the wild flow is varying, you change the controlled flow so that the ratio will be constant. I will try to make it faster. Okay, so these are the various schemes. You have feedback control, feed-forward control, you have cascade control, you have ratio control, and you have batch control. Okay, sometimes the process may be batch-wise, it may go. So you have batch control. Okay, so I have just given you a very brief idea about process control. Okay. Now we will quickly go into the second presentation. Sam, can we go to the second presentation, please? This is about the DCS and PLC. Okay, in industry, what we saw is process control. So you are all studying chemical engineer, means you will be studying a process control where you maintain the temperature or pressure or various process condition you control. Okay, so how you control the concept we have seen. Okay, so we have different concepts, we have different type of subsystems. You have sensors, controller, you have final control element, and the variations happen, load variation happens, you have manipulating some parameters, and so on. So we'll go to the next one. Here what we are going to study is, or try to understand is, the DCS or PLC. How in industry this process control can be done by you in a large scale. Because in a modern industry, if you go, some 20,000 of controllers are there. In my smelter, where I am working now, there are 50,000 instruments. Okay? So these are all controlled by automatic systems. So how it is controlled, we are going to see in the next presentation. So this is about the automation. As a chemical engineer, as an industrial engineer, you must know about this system, okay? So how automation is done in an industry in the point of view of process control. It's going to be very fast. I will not take too much time into it, okay? See, automation is used in mundane. It's mundane, you can say. It is used everywhere. It is used in chemical plants, all type of chemical plants, we are having automation. Oil and gas industries, even in metal processing industries. My dear friends, I would like to give this statement, why I became an instrumentation engineer. When I joined university, just like you as first year students, my professor told the importance of instrumentation. We are able to handle very dangerous chemicals and process because we have instrumentation and process control. We handle fluorides. He said, if a drop of fluoride you drop in the 20th floor of a building, the fluorine can pierce through all the floor and it can go down, and still it can go down and it can corrupt the environment. We have seen the cases of the Bhopal gas, where there was a big havoc. Poisonous chemicals, corrosive chemicals, we are able to handle because of the instrumentation and process control. So we have two types of instrumentation done in the industry. One is process control, controlling the process which we have seen. Another one is the safety system or emergency shutdown system, or we call it safety instrumented system. This safety instrumented system is becoming more and more important because we are having nuclear plants. And the nuclear plant, if anything goes beyond control, we need to shut down the process immediately and safely. It's very important. So the management of safety system is what we are now discussing today. It is more and more important because companies want to make more profit. They don't want their name to be spoiled. They don't want to pay huge amount of insurance. They want to be accountable to the society by keeping a safety instrumented system. Okay, so emergency shutdown system in oil pipelines, very important. Like this, we have many applications. This, I don't want to too much spend in that. What you see here is a camel, and you are seeing a vehicle. If you are driving, what you will do? You will work like an automatic control system. Your eyes will see the camel. Immediately what will happen? Your brain will give command to your legs, and you will apply brake. So you can see that this is exactly like a control system. Okay? You have the input module, your eyes are sensing, your brain is working as a control system, and legs are actuating and giving output to the brake and stopping the vehicle. Like valves, you have sensors, temperature, pressure, sensors are there. Okay? So this is an automatic system. Just giving you an analogy of a human being, his brain, we are having a controller which is automating the process with other equipments. Okay? So we have different kind of sensors which we have already seen in the previous presentation. These are common. We have many more parameters to be sensed. Okay? We have flow control, we have level control, okay? We have temperature control. Basically, in temperature control, you can control a temperature by using a steam or hot fluid circulating, or you can electrically, heat and you can control the temperature. So VFD is a heater bank, variable frequency drive you use, and you can control the temperature. Okay. You have pressure control systems. Okay. The concept is the same. You have a sensor, you have a controller, and you have a final control element which is actuating. Okay. And you have, in this way, you have many templates built into the automatic control system. Okay. So speed can be controlled. Okay, so in a DCS, in a distributed control system or automatic system, you are having various components. You have analog input, analog output. These are the modules which will take signal from the field. You have digital input. You have, in the digital input, if we are more specific, there are different type of digital inputs. We are not going into it. Okay. So analog signal is a continuous signal. I hope by now, because of the digital innovation, all of you must be understanding the difference between an analog and a digital. Okay? So analog means you will have a continuous voltage. You put a multimeter or you measure a voltage. Okay? So it's an analog value. it's a continuous variation. Okay? A digital is you are actually having a digital value in numbers. Okay? Basically, you will be using a analog to digital converter. You take the data and it can go into a computer as a numbers. Whereas analog value cannot go into a computer. If you give a voltage to the computer, it will burn. So digital data is a data which you need to convert into using analog to digital converter. Okay. So digital signals are there. You have the signals, some signals are 0, 1 kind of a signals. Okay, binary signals. Okay, analog signals can be, you can see here 4 to 20 milliamp. It is still a standard because finally the real life, we have everything in analog. In reality, you don't have a VGA or SVGA or XGA resolution. It is an analog. Okay, so we are having 4 to 20 milliamp is a standard for measuring the signals. Because why we are having 4 to 20 milliamp instead of 0 to 16? All are blank. Are you able to understand the question at least? See, you can see there, analog signal, the standard which is used for the DCS or whatever the equipments we use, we are having 4 to 20 milliamp. Why it is not 0 to 16? That is my question. Okay, okay. I will quickly, because this is actually, you are not pure instrumentation. The reason behind is, if I have 0 to 16, I will never know a failure of the instrument. Okay, because of some reason the power supply gone or equipment is not working. So equipment is not working, it will show 0. And the value is also 0, it will also, again it will be 0. You will not be able to differentiate. So we go for a 4 to 20 milliamp. 4 means 0, 20 means highest in the range. Okay? And we are having pneumatic signals also, 3 to 15 PSI and so on. Okay? What you see here is a DCS, distributed control system. In a DCS, we are having many, see, it is like a network. Okay, DCS is a network where you are having the control piece, controllers. We have the workstation for the operators. In the same network, the plant is also connected. So at different locations, the controllers also will be linked through this network. And in the end, you will be having a analog or digital modules which will convert the analog signals into digital and digital signal back into analog in the real world. Okay. So this involves many software. Okay, in order to configure this DCS, we have software to configure. Okay, we have software which will be running into the system that will be used for the operators to operate and so on. Okay, you have many software. You have software for keeping the data as a historian. You have the software for report generation. You have software for alarm management and so on. Okay, so this is a wide range of products used in the process control automation. Okay, I wanted to explain you the difference between the DCS and PLC. Because we are not having much time, I want to go into my main presentation. So what you should know is, see, DCS is a system where a lot of analog inputs can be handled. Okay, lot of analog process can be handled. Okay, but in a PLC, you may have a conveyor where most of the signals are digital or binary signals. And the number of IOs, number of input outputs may be less. Okay, so this is the difference between PLC and DCS. In the DCS, you can handle a lot of analog signals, and the total number of IOs may be very large. In a PLC, the IOs are lesser. In an industry where I was working in olefin plant, we were handling around 22,000 loops, control loops, which we have seen. Okay, whereas if we are using a PLC, maximum we can use maybe 10,000. Maybe 10,000 is a very high range. Maybe in thousands you can handle 2,000, 3,000 like that. And the applications may not be analog, it may be mostly the discrete kind of signals. Either it will be on, off, the position, limit switch, this kind of applications used in the PLC. Okay. We'll go to the next presentation. Yeah. Yeah, we are having many PLCs, like we are, see, if we are going for a safety application, we are calling it a Triconics PLC in Schneider Electronics. It is called the Triconics. The brand name is Triconics. And in Yokogawa, it is called ProSafe. So these are PLCs. Whereas DCS, if we see, Schneider is having a DCS called Foxborough. It's a one which is advanced. It can, in the same way you have Allen Bradley PLC, you have, which is PLC, but they are making it into a DCS by enhancing it. So different vendors are available who will be taking this automation as a project, and they will be executing this project. There will be EPCs and automation vendors. The EPC will give contract to the automation vendors, and automation vendors will do this. Okay. I think I would like to skip this presentation. Sam, we will go to the next presentation, please. See, basically, in this presentation of control valve, I wanted to explain you about the various control valves used in the industry, how the control valves are made fail-safe, and how they are working. But I will skip this one, we'll go to the next. Sam, can we go to the next presentation? After control valve. Yeah, okay. Now we are coming to the main topic. This is the one which we were discussing about, the management, life cycle management of the safety instrumented system. Okay, so we have not gone into the life cycle management. I'm giving you basically what is a safety instrumented system and how it is designed. Okay, so in order to provide the safety required for running an industry so that it will not affect the society, it will not give fatality to the people who are working, it will not affect the environment, it will not produce damage to the equipment. So we have safety system. Okay. So there are a lot of terminologies which we will be using in the safety system. Okay? Because of lack of time, I will explain you only, I will just give you the description of only few, like safety system means SIS, safety instrumented system. We call it SIS. Okay? An interlock function, which we have seen, we call it as SIF, safety instrumented function. And the required reliability of this function is defined by a term called SIL, safety integrity level. Okay? We call SIL, but when for people it is SIL, maybe they cannot understand, but it is talking about the integrity, safety integrity level. Okay. See, in an industry, we are having many layers of protection. Okay? So we are having a process is running. Okay? That means we have automatic process control system running in the background, automatically controlling the process. Okay? If the process is going beyond control, the DCS will provide alarms. And the operator will go and check and he will take action. So there is a process control and alarms in place. That is the first layer. Then in the second layer, if you see, you have the tripping system or safety instrumented system. So the safety instrumented system is also called, in the top if you see, second layer is the emergency shutdown system. So these are the systems which will avoid the happening of danger. This tripping, when it trips, the temperature or pressure will not go beyond the limit. So this is a prevention layer. The last layer of prevention is the safety instrumented system or the emergency shutdown system, which we are discussing about. Further, we are having the mitigation system. For example, you have a tank and the level control fail and the hydrocarbon or chemical is coming out. You have a wall called a dike wall around the tank, which will be mitigating only. It's not avoiding. Okay? You are having high pressure system, you are having the pressure regulating wall or PRV, like a mechanical device. Pressure gone high, but it will pop up and it will send the gas to the flare. That's the reason why you can see in some industries, sometime you will see the flare is going very high. Because some problem in the process and the PRV regulating valve, all the control system, everything fail and PRV open and it is going to the flare and it is burning high. Okay? So you have the mitigation. If all mitigation fail, you have emergency response, which is the last layer. So everything needs to be properly planned and it should be done in the industry. Okay. So we have various different names for this safety instrumented system. We call it ESD, fire and gas, burner management system, we have turbine machinery control system, and so on. These are all the various names of safety instrumented systems. Okay. Now coming to the safety instrumented system, we are having, this is different from the process control system. Okay. Basic process control system, DCS we have seen, that is different and this is different. Okay. So this system will trip, or it is called the emergency shutdown system, which will trip or stop the process. Okay. So you are having a pressure interlock. If the pressure goes beyond certain level, you have a pressure transmitter or a pressure switch, which will sense it and give the signal to the safety instrumented system or safety PLC. And the safety PLC will close this inlet valve so that the vessel will not be pressurized. Okay? So you have sensor subsystems, you have this whole thing is a safety instrumented system. You have subsystems like sensor, logic solver, and final element. All will be having failure probabilities. Okay, you have subsystems. The failure, if all the three should work together without failure, then only the system will trip in case of danger. So each has a probability of failure, and this probability of failure which we calculate and we try to mitigate. Okay, I'll skip this one. Okay. Here comes the safety and availability, which we were talking about. Okay, a safety system should be, it should be reliable. When I say reliable, there are two types of failure. One is the dangerous failure. When the pressure goes high, if the interlock is not working, what will happen? The vessel will burst. This is one kind of failure. Another failure, my colleagues are producing, there is heavy pressure from the management to produce more, but at that time, this instrument failed, and it is saying high pressure, and it is stopping the valve. It will not only stop the valve, it will stop the entire process. And the production will be lost for 1 hour. This is another kind of failure. Okay? So one is safety failure, another one is availability. Because of this failure, your availability is lost. Okay? So you have availability and you have safety. If both are enough, then your system is reliable. Okay? In order to do this, we are having redundancy to avoid in order to make it more safer and in order to make it available to avoid the spurious failures, we are having redundancy in the system. Okay? We are, instead of having only one sensor, we may have 2 sensors. Or you may have 3 sensors, and we will be having voting. It will not work if you are having 3 sensors. It will not work or it will not trip the plant if only one fails. Because one can fail because of the instrument fault. Okay? So you have a voting. When 2 are failing out of the 3, it will trip the plant. Okay? So these are the redundancies we use in the safety instrumented system, and we do the calculations for the probability of failure. Okay? So there is a response time for the process. The SIS should respond before the hazard happens. Okay? There is a time for that. Okay? And based on the risk of a process, we are actually categorizing the interlocks or the functions into 4 categories. Normally in the industries, we have 3 categories: SIL 1, SIL 2, SIL 3, in normal process industries. SIL 4 comes into picture in a nuclear industry. Okay? So depending upon the safety integrity level, we are trying to maintain the instrumented system. Okay? How we maintain the instrumented system? In order to have the integrity, okay, we have 2 kinds of failures: safe failure and dangerous failure. In order to maintain the integrity of the process, we are maintaining the system. Okay. We do the quantitative analysis, we do the risk assessment using the risk matrix, we take the probability of consequence and the probability of failure and the effect of consequence, and we categorize into SIL 1, SIL 2, SIL 3, 4 requirements. Okay? Then we do the risk. These are the methods for risk assessments. Okay? There are design methodologies to design this whole process. Okay? from the process control till emergency response. Okay? And in that, the safety instrumented system is provided the required SIL level, SIL 1, SIL 2, SIL 3, and it is designed with redundancy. Okay? So these are the probability of failure for different layers. Okay? When I say 1 into 10 power minus 1, it is you keep the integrity of this equipment or this system so that there can be one failure after 10 years. 1 into 10 power minus 1 means one failure in after 10 years. Okay? Like this is for SIL 1. SIL 2 means 100 year. SIL 3 means 1000 year. That much integrity we try to provide for the equipment. Okay? So we select the architecture. Architecture means what I told is the 1 out of 2, 2 out of 2 voting, the redundancy. Okay? We use different technologies. Sometimes we take a digital transmitter with diagnostics, and so on. Okay? So we design this. Okay? So how we maintain the integrity of a safety loop? Okay, we use smart transmitters. We avoid common cause failures. We don't have much time, so I'm just quickly telling. There's a common cause failure. We use diversity, we use diagnostics, we use redundancy in the design. Okay? And we calculate the probability of failure in our system for all the 3 subsystems. Okay? It is called the probability of failure, PFD average, for the whole system. Okay? We collect the data from if it is a new equipment, the manufacturer will give the information. Okay? In his manual, the probability of failure, diagnostics, all details will be available if you are using it for safety instrument system. Okay? Otherwise, industries like SABIC, Mahadin, we are having a database and we have the failure information. So from the failure information, we can find out the failure rate. Okay? Failure rate is number of failures divided by the mission time, or 1 upon MTBF. MTBF means mean time to fail. Okay? So these are the reliability tasks we do in the industry. We have a framework which will do this automatically. Okay? So why the life cycle management is important? If you see, a lot of accidents happen. 40% of the accidents happen at the time of commissioning. And accidents continues to happen throughout the lifetime of the industry. When it happens, because the commissioning time, they change the specification or give wrong specification, or in the operation stage, they do not do a proper maintenance. Systematically, they close some of the safety systems, or they buy again a specification problem, systematic, or due to the random failures. Okay, so failures can happen throughout the lifetime. So we need to maintain the integrity of the safety instrumented system. So we need a life cycle management of the safety instrumented system. So as I already told you about the standard IEC 61508, under which we have this standard for chemical industries, IEC 61511. This is for chemical industry. Okay, so this is talking about the life cycle management of the system, starting from the conceptual design, then execution of the project, then operation. During operation, you do some changes. Till it is decommissioned, there is a management required. The standard talks about the management how you keep it with integrity. Okay. Cell 1, cell 2. So these are some of the numbers continuously repeating it. And if you do it properly, it will not haunt you in case something happened wrong in the industry. Okay. So what we do is we are defining the design parameters. Again, we calculate the probability of failure on demand. And you can see the graph. The probability of failure is keep on increasing. When you do a maintenance, when you do a testing, again, the probability of failure come down and slowly it increases. The probabilities increases because of the random nature of the systems. Okay, so we give a recommendation through the systems in the safety instrumented in our framework. Okay, so I am in sort of time. This is actually very, if you go into it, you have a lot of things like the probability, the reliability, statistics, calculations. This is one of the things like the Markov process, which is used for systems which are more complicated. Okay, there are software, advanced softwares which are used in the industries, and there are because when redundant system, it becomes more complicated and the calculations become very numerous. Okay, so this is the introduction for safety instrument system. Since you are all staying here, I will go to the, in fact, we are not skipping much. The last presentation I am going to give, how in a case study, which you can see and we can close. Okay, Sam, we can go to the last presentation, number 7. The last one. Yeah. I appreciate all of you for staying with me. You're all hungry, I know. And also, I don't know about your restaurant's timing. Yeah. So don't worry, we are not missing much. I hope you understood what is process control and what is a safety instrument system we have seen. In fact, the safety instrument system is managed by those standards. There are some guidelines to maintain it. Like, for example, in our framework, what we do is we see that the standard is followed. For example, the process control is an independent network, and safety instrumented system is an independent network. It should not be connected. Okay, a failure in process control should not affect the safety system. It should be separate. The personnel working for the process control should be separate, and the safety system should be separate. From the design till operation, changes, everything is separate, should be separated out. And inadvertently, nobody should disable the safety system. So this is achieved by doing the proof testing intermittently, depending upon the risk of the process. This is what our system is, our framework is doing. So the framework will be doing a systematic risk assessment, classify the functions into SIL 1, SIL 2, SIL 3. And again, we will be, based on the probability of failure, it will decide the proof testing frequency. And the proof testing frequency will be implemented in the ERP or in the scheduling system. And you will test it, and the failures are recorded. Again, the recycle, when the review comes, the MTBF and all the actual values will be used for the calculation. Okay. Can we go to the next presentation? Yeah, this is the last presentation. Okay. Sam, this is presentation number 7. This is the last one. How we are managing a safety system in a MTBF, in a plant, in a hydrochemical plant of SABIC. how we are maintaining this, okay? So this is done in a petrochemical industry, okay? This particular study is done for the function of hydrocarbon, pressure interlock of hydrocarbon outlet header in a CATOFIN reactor. So in a CATOFIN reactor, we have catalyst, and the hydrocarbon is passed into this reactor and at a very high temperature and at a very high pressure, okay? And the reaction happens and the products are coming out, okay? The pressure should not exceed beyond that. So we are actually having a safety. There are 3 plants, similar functions available in these plants, okay? And you are having a hydrocarbon outlet header where you are having the pressure transmitter. The function name is given. SIF is the starting, the 3rd one, okay? It has a safety loop, okay? And HACCP is done. What is HACCP? In the design phase of the plant, we are doing a hazard and operability study, and based on that study, this interlock is designed, okay? So we refer this HACCP documents, and we verify whether this document is followed in the design and still it is existing, okay? Then we do a risk assessment again. So when we do the risk assessment, we get input from the chemical engineers, automation engineers, the safety personnel, operation personnel. We bring, it's a workshop, and we take all the information about the existing plant, okay? And these are the equipments. What you see here, which is called the tag names. In industry, each instrument or equipment will be called by a tag name, okay? What we do is, we take all this information, okay? We are putting it into the system, and we are documenting it, okay? What is the system? What are the tag names? What are the instrument involved in that? What are the safety requirement specification, okay? We document it in the system. Then we are putting the failure data, okay? We have already the MTBF of this instrument. We put the failure data into the system, okay? And also we are doing the layer of protection analysis, which is the risk assessment. And based on this risk assessment, we concluded that this particular function requires SIL 2, Safety Integrity Level 2. That means a failure can happen once in a 100-year only. After 100-year only, a failure can happen, okay? So that kind of integrity we are supposed to maintain, okay? We are putting the failure data into the system. We are giving the data for the sensor, controller, and final element, the valves. And we are calculating the PFD average. Okay, now what we see here is, at present, the instrument is, the function or the interlock as a whole is not meeting. It is giving SIL 1 only. It is integrity level 1 only it is providing. It's supposed to be 2. So we are giving recommendation, okay, we are giving some recommendation to use some smart devices in the recommendation. And again, based on this recommendation, if they implement, we are checking the integrity level or the PFD average. Okay, when we see that it is meeting, when you put this modification, it is meeting the requirement. Okay, based on this requirement, again we find out how often this need to be tested or maintained. It is 24 months. So we give a recommendation for proof testing interval, okay? This recommendation will be implemented in the ERP system, and regularly this will be tested in every 24 months, okay? This is about the yeah, this is about the integrity, whether it is meeting or not. Okay. Again, after we give the recommendation and it is implemented in ERP, the framework is having provision to record the test results, whether it is tested, whether it is deferred, not tested, all information we get from here. And the status is also coming here. Okay, so this is the place where you can put the result of the proof test. Okay. So this is a task which is repeating, which can be used to identify, because there are so many tests need to be done in the industry. Sometimes they may miss it. Okay, so we have a facility to find out how many due, how many deferred, like that. And the corporate level, they are able to see this status. Okay, because it is one of the KPI of the performance of the corporation or the industry. Okay, so a framework which I have shown you is used software called Meridium. Okay, in order to use this, you need the background about the safety instrumented system, the functions, the probability of failure, how to do this calculation, and so on. But basics you should know. The real thing is done by the software, which is configured. Okay. In fact, if you attend my paper presentation tomorrow, you may get a better view, because now you have some small finalities of the fine things of the safety system you understood. Tomorrow, I may not repeat these things, but you will get an overall picture, because I have implemented this system for SABIC, and from 2017, I'm trying to implement this system now nearly in the final stage for Madin Aluminium. So I had 2 case studies. Maybe tomorrow I will be having opportunity to present. I would request you to attend and get the full benefit of it. If you have any questions, you can ask me.
Yes, it's time for question and answers. Yes.
Next one.
Yeah, please. Can you mic? Yeah, very good question. Actually, this is a reliability engineer's question. See, we are actually having the failures called the bath curve tub, okay? And it is like a bathtub. It's called bathtub curve. But when we are doing reliability analysis, we are doing different functions, okay? Sometimes in our case, to be very fast for your question, we are using exponential data, exponential. They are having other curves also used in the reliability-centered maintenance. So these are all taken care of by the software, but one should be aware what is the difference between the exponential and the linear, and so on. Thank you.
And any other question? If there is no more questions, I would like to say thank you very much for your presentation, very comprehensive and complete theoretical explanation. Thank you very much. And yes, let's do sorry, thank you. And
thank you, Professor.
Thank you. And finally,
thank you, one and all.
Thanks.
Yeah.
And finally, I have an information for all of you. After lunch, there will be oral sessions, and they will be at the second floor. And for that reason, please prepare yourself. And if you can attend over there, it will be the oral presentation of some papers. That will be very exciting and extremely interesting. Thank you very much for your attendance, and see you very soon. Thank you. Bye now.